Look at any photograph of the night sky taken from a truly dark place, somewhere far from the glow of cities, and you will see a gentle chaos. Stars scattered like spilled salt, nebulae drifting in hazy patches of rose and violet. The Milky Way itself smeared across the frame in a band of soft light, its 100 billion suns blurring into milk. Everything looks random, organic. The universe appears to have been painted by a hand that favoured suggestion over precision, impression over geometry. Now consider that somewhere in that chaos, 600 million light-years away, there floats an object so geometrically perfect that when astronomers first saw it, they assumed their equipment was broken. A sphere. A ring. Both centred on the same point. The sphere made of old stars the colour of honey. The ring made of young stars the colour of ice. The two structures suspended around each other in near-perfect concentricity, as though someone had drawn them with a compass. And visible through the exact centre of this impossible arrangement, framed like a painting within a painting, sits a second ring galaxy, smaller, more distant, watching through the aperture like an eye. This is Hoag's object. It has been staring at us since 1950, and in 75 years of study no one has been able to explain how it exists. That last sentence is not poetry. It is a technical statement. The simulations cannot produce it. The physics does not predict it. When researchers run the numbers on galactic formation, on gravitational dynamics, on the ways matter clumps and collapses and spins into structure, the outputs are spirals and ellipses and irregular blobs. They are never this. Never a perfect core wrapped in a perfect ring with empty space between them like a moat around a castle. The math does not want to make this shape. And yet there it is, hanging in the constellation Serpens, 17 arc minutes across in our sky, a geometry lesson that nobody assigned. Over the next 2 hours we're going to sit with this object. We're going to trace its discovery, examine its structure, walk through the theories that have tried and failed to explain it, and confront the unsettling possibility that Hoag's object is not a mystery waiting to be solved, but a category error. A thing that slipped through the cracks between what the universe typically does and what apparently it can do when nobody is looking. If these slow, quiet journeys into the strange corners of space are something you find yourself returning to, consider tapping the like button. Consider subscribing. The algorithm notices and it helps others find their way here. Now settle in. Dim the lights if you haven't already. Let's begin. The year is 1950. The place is the Palomar Observatory, a white dome crouched on a mountain in Southern California like a temple to distant light. Inside, a man named Arthur Hoag is photographing the sky through the 48-inch Schmidt telescope, one of the most powerful wide-field instruments on Earth at the time. Hoag is not famous. He's not chasing a particular discovery. He's doing what astronomers in 1950 spent most of their time doing: cataloguing, surveying, building the patient archives that would let future generations ask better questions. On one of his photographic plates, among the thousands of dim smudges that represent galaxies too far away to resolve in detail, he notices something odd: a ring. Not a spiral scene edge-on, which can sometimes look ring-like. Not a lens flare or a photographic defect. A ring, perfectly circular, with a distinct central blob and empty space between the blob and the ring itself. The structure is so clean, so implausibly symmetric, that Hoag initially suspects he is looking at a gravitational lens, a phenomenon predicted by Einstein's general relativity, in which a massive foreground object bends the light of a background object into a ring shape. This would make the image an illusion, a trick of warped space-time, and the object itself would be something ordinary seen through extraordinary geometry. But the math doesn't work. For the ring to be a gravitational lensing artifact, the central blob would need to be enormously massive, far more massive than it appears, and the colour distribution is wrong. The ring is bluer than the core. In a gravitational lens, you would expect the light of the lensed object to be stretched and smeared, not neatly separated into two distinct populations of stars with different ages. Hoag publishes a short paper. The tone is puzzled, almost apologetic. He describes the object, notes that he cannot explain it, and essentially shrugs in print. The most likely interpretation, he writes, is that this is a ring of some kind, but its nature is entirely unclear. He names it nothing. He moves on. Other astronomers note its existence and also move on. For the next 2 decades, the object that would eventually bear Hoag's name sits in the catalogues like a typo nobody bothers to correct. Let that settle for a moment. One of the most geometrically perfect structures ever observed in the universe was discovered, photographed, published, and then essentially forgotten. Not because it was uninteresting, but because it was too interesting. So strange that no one knew what question to ask about it. This is how mysteries hide, not in the darkness between observations, but in the light of observations that make no sense. The data sits there, visible to anyone who looks, waiting for someone to realise that what they are seeing is impossible. To understand why Hoag's object is impossible, you first need to understand what a galaxy is supposed to look like. Close your eyes for a moment and picture the word galaxy. The image that comes to mind is almost certainly a spiral, a pinwheel of bright arms winding out from a central bulge, the whole structure tilted elegantly against the black. This is not an accident. The Milky Way is a spiral. Andromeda, our nearest large neighbour, is a spiral. The most photogenic galaxies in every coffee table astronomy book are spirals. We have trained ourselves to see this shape as the default, the norm, the way a galaxy is supposed to be. But spirals are only about 30% of all galaxies. The most common type by far is the elliptical, a smooth, featureless blob of old stars ranging in shape from nearly spherical to elongated like a cigar. Ellipticals contain little gas and dust. They form few new stars. They are, in a sense, galaxies that have finished their business and settled into quiet retirement. Then there are the irregulars, galaxies with no discernible structure at all, often the result of recent collisions or gravitational disruptions. The Magellanic Clouds, visible from the southern hemisphere, are irregulars, ragged patches of stars torn into a symmetry by their dance with the Milky Way. And then, rarest of all, there are the ring galaxies. A ring galaxy is exactly what it sounds like, a galaxy in which the stars are arranged in a ring rather than a disk or a blob. They are uncommon. Of the billions of galaxies we have catalogued, only a few hundred are classified as rings, and nearly all of them share a single formation story: collision. Picture 2 galaxies approaching each other in the void. One is a standard spiral, with a central bulge and a flat disk of gas and stars. The other is smaller, denser, perhaps an elliptical or a compact dwarf. As the smaller galaxy passes through the centre of the larger one, not a glancing blow, but a direct puncture through the middle, it sends a shockwave rippling outward through the disk. The gas compresses. Star formation ignites in a ring that expands like the ripple from a stone dropped into still water. The central bulge remains, but the disk is now a ring, blue with newborn stars pushed outward by the gravitational disturbance of the intruder. This is called a collisional ring galaxy, and the most famous example is the Cartwheel Galaxy, 400 million light-years away in the constellation Sculptor. If you have seen a photograph of a ring galaxy before, it was probably the Cartwheel, a brilliant blue ring surrounding a bright core with faint spokes of material still connecting the two like the remnants of a shattered wheel. Now here is the problem with Hoag's object. It does not look like a collisional ring. The ring is too perfect, the core is too centred, the gap between them is too clean, and most damning of all, there is no intruder, no companion galaxy nearby that could have punched through the centre and caused the ripple. No tidal streams or debris trails suggesting a recent gravitational interaction. No asymmetries, no warping, no evidence of violence at all. When astronomers examine a collisional ring like the Cartwheel, they find chaos beneath the beauty. The ring is not quite circular. The core is slightly offset. There are streamers and knots and density variations that record the history of the impact. The ring galaxy is a crime scene, and the evidence of the crime is everywhere. Hoag's object has no evidence. It is a ring galaxy with no apparent cause, a crime scene scrubbed clean. This is the first layer of the geometric horror. The shape exists, but the process that should have created it is missing. Let me give you a sense of scale before we go further. Hoag's object is approximately 100,000 light-years in diameter. That is roughly the same size as the Milky Way. If you could somehow travel there, if you could hang in space a few 100,000 light-years out and look back at this structure, you would see something that fills the sky the way our own galaxy would fill the sky. A vast, silent architecture of light, too large to comprehend as a single object. The central core is about 17,000 light-years across. It contains old stars, yellow and orange, some of them as ancient as 10 billion years. These are population 2 stars, the kind that formed early in cosmic history when the universe was still rich in hydrogen and helium, but poor in the heavier elements that would later be forged in stellar cores and scattered by supernovae. The core of Hoag's object is, in other words, a relic, a fossil, a chunk of the early universe suspended in the present like an insect in amber. Now travel outward from that core. You cross a gap, a void, a region of space almost entirely empty of stars, stretching for roughly 9,000 light-years. This is not a thin transition zone. This is a moat, a gulf, a distance greater than the span from our Sun to the nearest 10,000 stars in our local neighbourhood. And in Hoag's object, this distance contains almost nothing. On the other side of the gap you reach the ring. The ring is blue, brilliantly, unmistakably blue. It is made of young stars, some of them only a few 100 million years old, infants by cosmic standards. These are population I stars, born from gas that has been enriched by generations of earlier supernovae. They burn hot and fast. They will die within 1 billion years, but for now they blaze with the fierce light of youth, forming a circle of ice around the amber core. The ring is approximately 15,000 light-years wide. It is not uniform. There are knots and density variations, regions where star formation is more active, regions where it has paused. But these variations are subtle. The overall shape is circular to within a few percent. The ring is centered on the core to within the limits of measurement. The alignment is so precise that when astronomers model it mathematically, they have to use the language of engineering rather than the language of nature. Stop and feel the weight of that. A structure the size of our entire galaxy, sitting 600 million light-years away, arranged in a geometry so clean that it looks designed. Not evolved, not collapsed, designed. As though someone placed the pieces with care, stepped back, and admired the symmetry. And then, because the universe has a sense of humour that borders on cruelty, there is one more detail. Visible through the centre of Hoag's object, framed perfectly in the gap between the core and the ring, is a second ring galaxy. It is smaller. It is more distant. No one knows exactly how much more distant, but it is clearly a background object, not a companion. It hangs in the aperture like a portrait in a frame, a ring within a ring, an echo of the structure that contains it. The odds of this alignment are incalculable, not impossible. With enough galaxies scattered across enough of the sky, coincidental alignments will happen, but the psychological effect is undeniable. Hoag's object does not merely exist as a geometric anomaly. It exists as a geometric anomaly that contains a smaller geometric anomaly, visible through its centre, as though the universe were making a point about circles that we are not clever enough to understand. The first serious attempt to explain Hoag's object came in the 1970s, when astronomers began to have access to better instruments and more detailed observations. The question was straightforward. If this is not a collisional ring, what is it? The leading alternative theory was accretion. Here is the idea. Imagine a galaxy that forms normally, a central bulge of old stars, perhaps the remnant of an early elliptical structure. Now imagine that this galaxy, over billions of years, slowly accumulates gas from its environment. Intergalactic space is not perfectly empty. There are thin filaments of hydrogen, remnants of the cosmic web, tendrils of matter left over from the early universe. If a galaxy sits in the right place, it might gradually pull this gas inward, forming a disk around itself. But disks, under normal circumstances, connect to their central bulges. Gas flows inward, forms stars, spirals down toward the centre. The result is a spiral galaxy, not a ring. For the accretion theory to work, something would have to prevent the gas from reaching the core. Something would have to maintain that 9,000 light-year gap. One proposal involved a bar. Many spiral galaxies have a bar, a linear structure of stars running through the centre of the galaxy, connecting the nucleus to the spiral arms. Bars are common, perhaps present in 2/3 of all spirals, and bars, through their gravitational influence, can carve out gaps in the surrounding disk. They can sweep material away from certain regions, concentrating it at specific radii. Perhaps, the theory went, Hoag's object once had a bar. Perhaps the bar maintained the gap while the ring accumulated. And perhaps, over time, the bar dissolved, leaving only the ring and the core behind. It was a clever idea. It was also wrong. When astronomers examined Hoag's object in near-infrared light, which penetrates dust and reveals the distribution of old, low-mass stars that make up the structural backbone of a galaxy, they found no evidence of a bar. Not even a faint one. Not even a residual structure that might have once been a bar. The core of Hoag's object is smooth, spherical, featureless. It is an almost perfect elliptical galaxy, sitting at the centre of a ring that has no business being there. The bar theory collapsed. The next attempt involved dark matter. Every galaxy is embedded in a halo of dark matter, a vast invisible cloud of particles that interact with ordinary matter only through gravity. The dark matter halo extends far beyond the visible galaxy, sometimes 10 times the diameter of the luminous disk. It provides the gravitational scaffolding on which galaxies form and shapes the dynamics of their rotation. Perhaps, the new theory proposed, Hoag's object has an unusual dark matter distribution. Perhaps the halo has a density profile that creates a kind of gravitational well at a specific radius, encouraging gas to collect in a ring rather than a disk. Perhaps the shape we see is not imposed by collision or by bars, but by the invisible architecture of the dark matter itself. This theory is harder to test. Dark matter, by definition, does not emit light. We infer its presence from its gravitational effects, from the rotation curves of galaxies, from the bending of light around galaxy clusters, from the large-scale distribution of cosmic structure. Measuring the dark matter profile of a single galaxy, 600 million light-years away, is extraordinarily difficult. But the theory has a problem. It is, in a sense, too flexible. You can propose almost any dark matter distribution you like to explain any observed structure. The theory explains everything, and therefore explains nothing. It is a mathematical description of the shape, not a physical explanation of how the shape came to be. And there is a deeper issue. Even if the dark matter halo has an unusual profile, you still need to explain where the gas came from. You still need to explain how a ring of young blue stars formed around a core of ancient yellow stars without any evidence of recent interaction. You still need to explain the gap. The dark matter theory did not collapse. It simply faded into the background, a placeholder rather than a solution. By the 1990s, Hoag's object had been elevated from a curiosity to a genuine puzzle. The Hubble Space Telescope, launched in 1990, provided images of unprecedented clarity. For the first time, astronomers could resolve individual stars and star-forming regions within the ring. They could measure the colours and ages of different components with precision. They could build detailed models of the object's structure. What they found only deepened the mystery. The ring is not a single structure. It contains multiple knots of active star formation, separated by quieter regions where older stars dominate. The star formation is not uniform. It is episodic, as though the ring has experienced bursts of activity at different times, separated by millions of years of relative calm. This suggests that the ring is not simply a static feature, but an evolving one, fed by gas that arrives in pulses rather than a steady stream. But where is the gas coming from? The intergalactic medium around Hoag's object appears normal. There are no obvious filaments or streams feeding into the ring. There are no nearby galaxies close enough to be donors. The gas that fuels the ring's star formation seems to come from nowhere, appearing at the ring's location, igniting into stars and leaving no trace of its origin. This is the second layer of the geometric horror. Not only does the shape lack an explanation, but the fuel that maintains the shape lacks an explanation as well. Hoag's object is not merely a strange structure, it is a strange structure that is actively doing something strange, right now, in a way that no one can account for. Some astronomers began to suggest cautiously that Hoag's object might be unique. Not unique in the sense that it is the only ring galaxy, but unique in the sense that it might require a unique explanation. A set of initial conditions and evolutionary processes so specific, so improbable, that they have occurred only once in the observable universe. This is an uncomfortable position for science. Science prefers general explanations. It prefers theories that account for classes of objects, not individual exceptions. If Hoag's object can only be explained by invoking a 1 in a trillion coincidence, then we have not really explained it at all. We have simply given up. But the alternative is even more uncomfortable. If Hoag's object is not unique, then there should be others like it, and there are not. In 75 years of searching, astronomers have found a handful of ring galaxies with vaguely similar morphology, but none with the same combination of features: the perfect circular symmetry, the clean gap, the old core, the young ring, the absence of any companion or debris. Hoag's object remains, as far as we can tell, alone. There is a feeling that comes when you sit with an object like this for long enough, a feeling that the universe is not quite as tidy as we like to pretend. We tell ourselves stories about how galaxies form. We run simulations on supercomputers, seeding them with the initial conditions of the early universe, and letting gravity and gas dynamics and dark matter do their work over billions of simulated years. The outputs look familiar: spirals and ellipticals and irregulars, the zoo of galactic morphology that we observe all around us. We feel confident. We feel that we understand. And then we encounter Hoag's object, and the simulations cannot produce it. Not reliably. Not without adjusting the parameters by hand, without fine-tuning the initial conditions until the desired shape emerges. The ring appears in the simulations only when we force it to appear. When we run the simulations honestly, with random initial conditions and standard physics, the ring does not form. This is what I mean by geometric horror. Not horror in the cinematic sense, not fear or revulsion, but the quieter horror of confronting a shape that should not exist. The horror of realizing that our models, our careful, tested, successful models, have a blind spot, a gap, a region of possibility that they cannot reach. Hoag's object is not alone in this. There are other anomalies scattered through the cosmos, other structures that challenge our understanding in ways we cannot easily dismiss. But Hoag's object is special because it is so obvious. It is not a subtle deviation from prediction. It is not a 1% discrepancy that requires careful statistical analysis to detect. It is a perfect ring around a perfect sphere, glowing in the dark 600 million light-years away, daring us to explain it. We have been dared for 75 years. We have not succeeded. Let me return to the image for a moment. The image is what stays with you, long after the numbers and the theories fade. Picture yourself floating in space, far enough from Hoag's object to see the whole structure at once. The core is before you, a soft golden glow, its light travelling 600 million years to reach your eyes. Around it, separated by a dark gulf, the ring burns blue, a circle of new stars so bright and so young that they outshine the ancient core despite containing a fraction of its mass. The two structures do not touch. They do not blend. They exist in perfect isolation, connected only by gravity, separated by a void that should not be there. And through the centre, through the dark aperture at the heart of it all, you can see another ring, smaller, fainter, more distant. A second geometry nested within the first, like a reflection in a mirror that reflects only circles. There is no sound. There is no movement you can perceive. The stars burn in silence. The ring hangs motionless against the black. But you know, because you have read the papers and run the calculations, that this structure is doing something. The ring is forming stars. The gas is flowing from somewhere. The system is alive in its slow cosmic way, maintaining a shape that physics does not prefer. You watch. You wait for an explanation. None comes. This is what it feels like to encounter Hoag's object. Not frustration exactly. Not awe exactly. Something between the two. Something that partakes of both. A recognition that the universe is larger than our models, stranger than our intuitions, and patient beyond all human comprehension. The ring has been there for at least 2 billion years. It will be there for billions more. It does not care whether we understand it. It does not care whether we try. It simply exists. A circle around a sphere. A ring around a core. A shape that should not be. Floating in the dark, waiting for someone clever enough to explain it. We are not that clever yet, but we are getting closer. And in the chapters that follow, we are going to trace every attempt, every theory, every failure, until we stand at the edge of what is known and look out at what remains unknown. We are going to learn what Hoag's object has taught us about galactic dynamics, about gravitational interactions, about the limits of simulation and the humility of science. And then, at the end, we are going to sit with the silence that remains when all the theories have been tried and none of them have worked. That silence has a shape. It is the same shape as the object itself, a ring, a sphere, a gap between them that no one can explain. Before we go further into the science, I want you to understand something about the people who study objects like this. They are not mystics. They are not easily impressed. The average professional astronomer has spent years learning to be skeptical, learning to demand evidence, learning to distrust their own intuitions and the intuitions of their colleagues. They have seen 1,000 anomalies turn out to be instrument errors. They have watched 100 impossible observations dissolve into ordinary phenomena once the data was examined more carefully. When these people tell you that Hoag's object is genuinely strange, they are not being poetic. They are making a technical assessment based on decades of experience, and they are admitting, in the careful language of science, that they do not know what they are looking at. This matters because it is easy, in the age of clickbait and sensationalism, to become numb to claims of mystery. Everything is presented as shocking, as mind-blowing, as paradigm-shattering. The words lose their meaning. The mysteries become noise. Hoag's object is not noise, it is signal. It is a clear, persistent, 75-year-old signal that something in our understanding of galactic formation is incomplete. Not wrong, necessarily, but incomplete. There is a gap in our models, a shape they cannot produce, and that gap has a name and a location and a photograph. The photograph is beautiful, the gap is real. Both of those things are true at the same time. In 2012, a team of researchers led by Noah Brosh at Tel Aviv University published what remains one of the most detailed studies of Hoag's object to date. They used data from multiple telescopes operating at different wavelengths, building a comprehensive portrait of the object's structure and composition. Their findings were meticulous. They confirmed that the core is composed of old, metal-poor stars with an age of approximately 10 billion years. They confirmed that the ring is composed of young, metal-rich stars with ages ranging from a few 100 million to perhaps 2 billion years. They measured the rotational velocity of the ring and found it consistent with a standard galactic rotation curve, suggesting that the ring is dynamically stable and has been for a long time. But when they tried to construct a formation history, a story that would lead from the early universe to the structure they observed, they could not do it. Not with standard scenarios, not with any single model. They considered the collision hypothesis and rejected it for the reasons we have already discussed. No evidence of an intruder, no asymmetries, no debris. They considered the accretion hypothesis and found it insufficient. No mechanism to maintain the gap, no explanation for the episodic star formation, no source for the gas. They considered the bar dissolution hypothesis and found no evidence that a bar had ever existed. In the end, they concluded that Hoag's object remains one of the most puzzling galaxies known, and that its formation remains an open question. This is the language of science when science has no answer. Not a declaration of defeat, but an acknowledgement of limits. An invitation for future researchers to try again, with better data, with new ideas, with the next generation of simulations. That invitation has been open for over a decade. It remains unclaimed. There is one more detail I want to leave you with before we pause, one more fact that makes the geometric horror complete. Hoag's object is not perfectly face-on to us. It is tilted slightly, by about 20 degrees from perpendicular. This means that the ring we see is not perfectly circular. It is slightly elliptical, foreshortened by our viewing angle. When astronomers correct for this tilt and calculate the true shape of the ring, they find something remarkable. The ring is circular to within 1%. 1%, a structure 50,000 light-years across made of gas and dust and stars, shaped by gravity and dark matter and the accumulated chaos of billions of years, and it deviates from perfect circularity by 1%. For comparison, Earth's orbit around the Sun is an ellipse with an eccentricity of about 1.5%. The ring of Hoag's object is more circular than Earth's orbit. It is more circular than most structures we encounter anywhere in nature. It is circular in a way that feels intentional, even though we know that no intention was involved. Or do we know that? That is the question that haunts the edges of this mystery. Not the serious scientific question, which assumes natural causes and seeks to identify them, but the older question, the question that whispers in the back of the mind when the lights are low and the night is long. Why is it so perfect? We do not know. We cannot answer that question with science, because science does not deal in intentions. Science deals in processes, in mechanisms, in the blind operation of physical law. If a ring forms that happens to be circular, science asks how, not why. But the human mind asks why. It cannot help itself. It sees a pattern, especially a pattern this striking, and it reaches for meaning. It wants the shape to signify something. It wants the perfection to be purposeful. Hoag's object offers no purpose. It offers only itself. A ring, a sphere, a gap, a second ring visible through the first. A geometry lesson with no teacher. A puzzle with no solution. And it is with that puzzle, that silence, that beautiful and terrible perfection, that we will sit for the remainder of this journey. We have met Hoag's object. We have seen its shape and learned its dimensions. We have surveyed the theories and watched them fail. Now we go deeper. Now we ask the harder questions. Now we examine the simulations that cannot produce it, the physics that does not predict it, the galaxy formation models that break against its geometry like waves against a cliff. The cliff does not move. The waves keep coming. There is more to learn. There is more to fail to understand. Let me begin with a confession about simulations. When astronomers build computer models of the universe, they are doing something profoundly strange. They are taking the equations of physics, equations that describe how gravity pulls, how gas cools, how stars ignite, how dark matter clumps invisibly around visible matter, and they are setting those equations loose in a digital space. They create initial conditions, press play, and watch. They watch for the equivalent of billions of years. They watch matter fall together, galaxies form, collide, merge, tear apart, reform. They watch the universe unfold according to the rules they have given it. And then they compare what emerges to what we actually see. This is how we test our understanding. If the simulations produce galaxies that look like real galaxies, spirals with the right number of arms, ellipticals with the right brightness profiles, the right distribution of sizes and shapes and colours, then we conclude that our physics is probably correct. That we understand, at least in broad strokes, how galaxies come to be. The simulations have gotten remarkably good. Over the past 3 decades, they have reproduced the cosmic web, that vast network of filaments and voids that structures the universe at the largest scales. They have reproduced the abundance of different galaxy types. They have reproduced the way galaxies cluster, the way they spin, the way their rotation curves flatten in ways that require dark matter to explain. But there are things the simulations do not produce. Hoag's object is one of them. I want you to understand what this means, because it is easy to dismiss, easy to say, well, the simulations are imperfect, and of course there are outliers, and we cannot expect models to capture every strange thing that nature creates. All of that is true, but there is a difference between a simulation that fails to produce common objects and a simulation that cannot produce a specific object even when specifically instructed to try. Run a galaxy formation simulation with standard initial conditions, the kind of conditions that should exist throughout the universe, and you will produce millions of galaxies. Spirals, ellipticals, irregulars, dwarfs, giants. You will produce merging galaxies and interacting galaxies and galaxies in clusters and galaxies in isolation. You will produce rings, occasionally, when conditions are right. What you will not produce is Hoag's object, not once, not in millions of simulated galaxies, not in the most sophisticated simulations we have ever built. The Illustris project, which ran in the early 2010s, simulated a cube of universe roughly 350 million light-years on a side. It tracked dark matter, gas, stars, magnetic fields, supermassive black holes, and the feedback effects of supernovae and active galactic nuclei. It produced over 40,000 galaxies. Some were spirals, some were ellipticals, some were peculiar. None looked like Hoag's object. The Illustris TNG project, its successor, used improved physics and higher resolution. It produced even more galaxies with even more realistic properties. Star formation histories that matched observations, colour distributions that matched observations, rotation curves, metallicities, morphologies, all matching. No Hoag's object. The Eagle project, run by a different collaboration using different code and different assumptions about feedback processes, produced another comprehensive survey of simulated galaxies, thousands upon thousands of them, spanning the full range of masses and environments and merger histories. Still no Hoag's object. You might think this is merely a statistics problem. Hoag's object is rare. We know of perhaps a few hundred ring galaxies in the observable universe, and Hoag's object is unusual even among those. Perhaps we simply need bigger simulations, more galaxies, a wider net. But this misses the point. The problem is not that we need more tries. The problem is that when researchers specifically attempt to create Hoag-like objects in targeted simulations, when they deliberately set up initial conditions designed to produce empty core ring galaxies, they still cannot reliably generate the geometry we observe. Let me be precise about what they have tried. In collisional ring galaxy simulations, researchers place a small intruder galaxy on a collision course with a larger disk galaxy. They vary the mass ratio, the impact parameter, the velocity, the angle of approach. They run the simulation and watch the ring expand outward from the impact point like a ripple in a pond. The rings they produce are real. They match real ring galaxies. The Cartwheel, ARP-147, others. Collisional ring formation is well understood and well simulated. But the rings are asymmetric. They are off-center relative to the core. They show tidal tails and debris streams. They show the intruder, either embedded in the disk or escaping on the other side or orbiting back for another pass. They look like the aftermath of violence because they are the aftermath of violence. Hoag's object shows none of this. Its ring is centered. Its core shows no displacement. There is no intruder, no debris, no sign of the impact that would have been required. When researchers try to produce a Hoag-like object through collision, they must fine-tune the parameters to absurd precision. The mass ratio must be just so. The impact angle must be exactly perpendicular. The intruder must be entirely absorbed without a trace. And even then, even with perfect fine-tuning, the resulting ring is not stable. It does not maintain its shape over billions of years. It spreads, distorts, or dissipates. What about bar instability simulations? Here, researchers create a disk galaxy with a strong central bar and watch what happens as the bar transfers angular momentum to the outer disk. Bars can dissolve over time, leaving behind structures that resemble lenses or rings. Some ring structures do emerge from these simulations, but they emerge at the wrong radius, with the wrong density profile, in the wrong relationship to the core. Bar-driven rings tend to be inner features, close to the nucleus, not vast structures at the outer edge of the stellar distribution. They are also typically accompanied by other morphological features, oval distortions, nuclear rings, resonant structures, that Hoag's object does not display. What about accretion scenarios? Here, researchers model a galaxy gradually accumulating gas from its environment, from filaments of the cosmic web, from minor satellites, from cooling flows. They watch the gas settle into a disk, form stars, and potentially create ring-like structures. These simulations can produce extended gas disks. They can produce star-forming rings, but they cannot explain the gap. The gap is the problem. A galaxy that is accreting gas will have gas throughout its disk, not only in a narrow outer ring separated from the core by tens of thousands of light-years of empty space. The dynamics do not permit it. Gas falls inward. It does not hover at a specific radius and refuse to proceed, unless something stops it. Unless there is a mechanism, a barrier, a process that clears the intermediate zone and keeps it clear. Dark matter, perhaps? This is one of the more speculative directions that researchers have explored. In the standard model of galaxy formation, dark matter halos are not perfectly smooth. They are lumpy, filled with substructure, with smaller clumps and streams and the remnants of past mergers. These substructures affect the dynamics of the visible matter. They can create resonances, gravitational features, regions where gas accumulates, or regions where gas is excluded. Could Hoag's object have an unusual dark matter halo? A halo with a specific density profile that creates a resonance at exactly the radius of the ring? A halo that somehow maintains a cleared zone through gravitational dynamics alone? This is not impossible, but it is ad hoc. It requires a dark matter configuration that we have no independent evidence for, producing effects that we have no other examples of, in exactly one galaxy out of the trillions we observe. It explains the mystery by invoking a deeper mystery. It pushes the question back one level without answering it. This is the pattern. Every explanation proposed for Hoag's object either fails to match the observations or requires special circumstances that themselves demand explanation. The simulations do not produce it naturally. The targeted attempts produce approximations that fall short. The theoretical framework suggests possibilities that remain unconfirmed, and through it all, the galaxy sits there, 8 billion light-years away, but only 600 million in apparent position thanks to the light travel time. Its ring 1% away from perfect circularity, its gap empty and unexplained, its geometry a rebuke to our models. I want to tell you about a specific simulation experiment because it illustrates the depth of the problem. In 2011, a team of researchers decided to approach the Hoag's object problem systematically. They built a series of simulations designed to test whether any plausible formation scenario could produce the observed morphology. They varied parameters across hundreds of runs. They tracked the evolution of ring structures over billions of simulated years. They measured gap widths, ring circularities, core properties, and long-term stability. Their conclusion, published in a paper that has been cited many times since, was sobering. They found that collisional scenarios could produce ring galaxies, but not stable ones with centered cores. They found that bar dissolution scenarios could produce nuclear rings, but not outer rings with wide gaps. They found that accretion scenarios could produce extended gas disks, but not the episodic star formation profile required. They found, in short, that no standard formation mechanism could reliably produce Hoag's object. But here is the part that matters. In their final analysis, the researchers noted that one scenario did produce a Hoag-like morphology. A scenario they called idealized and acknowledged was not obviously physical. In this scenario, they simply placed a ring of gas at a specific radius around a core and let it evolve in isolation. No collision, no bar dissolution, no accretion, just a ring, appearing from nowhere, maintained by nothing. The ring remained stable, it formed stars, it maintained its circularity, it looked like Hoag's object. The researchers were careful to note that this was not a formation scenario. It was a stability test. It showed that a Hoag-like structure could persist once formed, but it said nothing about how it could form in the first place. The ring had to be placed there by hand, by the researchers themselves, in their simulation as an initial condition. This is what I mean by geometric horror. Not that the object is impossible, but that the path from standard physics to this specific geometry remains invisible. The simulations can maintain Hoag's object but cannot create it. They can describe its present but not explain its past. They can measure its perfection but not account for it. It is as if we found a perfectly spherical boulder on the moon and could demonstrate that a sphere will remain stable on a flat surface, but could not identify any process on the moon that could carve a perfect sphere from lunar rock. The sphere exists. The sphere is stable. The sphere should not be there. Now I want to take you somewhere else for a moment, somewhere that might seem unrelated but is not. In mathematics, there is a concept called fine-tuning. It refers to situations where a system's behavior depends sensitively on the precise values of its parameters. Change a number by a tiny amount, and the outcome changes dramatically. The system is balanced on a knife's edge, and we are left asking why it happens to be balanced there. Physicists encounter fine-tuning problems throughout their discipline. The cosmological constant, the energy density of empty space, appears to be fine-tuned to an extraordinary degree. The masses of fundamental particles appear to be fine-tuned in ways that permit complex chemistry and life. The initial conditions of the universe appear to be fine-tuned to produce a cosmos that is neither too smooth nor too clumpy for structure to form. These fine-tuning problems are controversial. Some physicists see them as profound mysteries requiring new physics to explain. Others see them as artifacts of our ignorance, problems that will dissolve when we understand the deeper principles that determine these values. Still others invoke the anthropic principle, the idea that we must observe a universe compatible with our existence, so of course we see the fine-tuned values that permit observers. I mention fine-tuning because Hoag's object presents its own version of the problem, not a fundamental physics problem, not a cosmological problem, but a morphological fine-tuning problem at the scale of a single galaxy. The geometry is too precise to emerge from typical processes. The ring is too circular, the gap too clean, the core too centered. To produce this structure through any proposed mechanism requires fine-tuning the initial conditions, the mass ratios, the impact angles, the accretion rates, the dark matter profile, to degrees that seem unlikely without some deeper organizing principle. But what organizing principle? Gravity does not favour perfect circles. Gravity produces ellipses, spirals, blobs, streams. It produces structures that are good enough, stable enough, but rarely geometrically ideal. The perfection of Hoag's object is not what gravity would predict. It is not what chaos would predict. It is not what any natural process we understand would predict. And yet there it is. Some astronomers, when pressed, will admit that they find Hoag's object unsettling precisely because of this. Not unsettling in a way that challenges their scientific worldview. They remain confident that some natural explanation exists, but unsettling in a visceral, aesthetic way. The symmetry is too good. The geometry is too clean. It looks, they will say quietly, designed. They do not mean this literally. They do not invoke designers or intelligences or any supernatural agency. They mean it as a description of their psychological response to the object. It triggers the pattern recognition systems in the human brain that evolved to detect intention. It looks like something made, even though we know it was not made. This is the geometric horror I have been circling around. Not that Hoag's object violates physics. It does not. Not that it requires magic. It does not. But that it sits in a conceptual, uncanny valley between the random and the designed, between the explicable and the mysterious, between what our models predict and what our eyes see. Let me give you another number to sit with. The probability of a collisional ring galaxy forming with the specific properties of Hoag's object, the centered core, the circular ring, the clean gap, the absence of any intruder or debris, has been estimated by various researchers at different times. The estimates vary widely because they depend on assumptions about initial conditions, about the frequency of different collision geometries, about the distribution of galaxy masses and velocities. But even the most generous estimates place the probability somewhere below 1 in 10 million. 1 in 10 million for a single galaxy. One specific set of initial conditions, one specific collision geometry, one specific merger history out of all the mergers that have occurred in the observable universe. Now consider how many galaxies we can observe, roughly 2 trillion give or take. Consider how many ring galaxies we find among them, perhaps a few hundred. Consider how many of those few hundred show the specific Hoag-like morphology, perhaps a handful, perhaps a dozen, depending on how strictly you define the category. Is 1 in 10 million consistent with observing a handful of Hoag-like objects in 2 trillion galaxies? Mathematically, yes. Barely. The numbers can be made to work if you are willing to accept that Hoag's object and its cousins are simply the extreme tail of a distribution, the lucky few that happen to satisfy all the conditions required. But this is the fine-tuning problem in another guise. The mathematics permits it, but the intuition rebels. The explanation feels unsatisfying, like explaining a royal flush by noting that it has the same probability as any other specific hand. Technically true, but somehow missing the point. The point is that Hoag's object does not look like luck. It looks like precision. It looks like something that was supposed to happen, not something that accidentally happened. And our scientific framework has no room for supposing, no mechanism for precision beyond the blind workings of physical law. So we are left with a choice. We can accept that Hoag's object is simply an extreme statistical outlier, a lottery winner in the cosmic sweepstakes of galactic morphology, formed by a process we understand in principle but could not replicate in practice. Or we can suspect that something is missing from our models, some mechanism or principle that we have not yet identified, something that makes Hoag-like structures more likely than our current simulations suggest. Most astronomers, if they think about it at all, lean toward the second option, not because they have evidence for a missing mechanism, but because the alternative, pure improbable luck, feels intellectually unsatisfying. Science progresses by explaining, not by accepting. When we encounter something that appears fine-tuned, we look for the tuner, even if the tuner turns out to be nothing more exotic than a physical process we had overlooked. But no one has found the tuner for Hoag's object. No one has identified the missing mechanism. The 75-year search continues, and the galaxy continues to sit there, perfect and unexplained, a geometry lesson with no teacher. I said earlier that we would examine the physics that does not predict Hoag's object. Let me be more specific about what I mean. In the standard model of galaxy formation, galaxies grow hierarchically. Small structures form first, collapsing out of the primordial gas under the influence of dark matter gravity. These small structures merge to form larger structures. Larger structures merge to form still larger structures. The process continues over billions of years, building ever more massive galaxies from the accumulated debris of countless smaller ancestors. This hierarchical assembly is chaotic. Mergers happen at random angles with random velocities, with random mass ratios. The resulting galaxies are shaped by this history, twisted, distorted, stirred by the violence of their past. Elliptical galaxies in particular are thought to be the products of major mergers, their smooth, featureless shapes the result of thorough dynamical mixing that erases any memory of the original progenitors. Spiral galaxies, by contrast, are thought to have quieter histories. They are galaxies that have avoided major mergers, allowing their disks to remain intact, their spiral structure to persist. But even spiral galaxies show the scars of minor interactions, warps, asymmetries, streams of stars torn from satellite galaxies and still orbiting in the halo. Hoag's object fits neither paradigm. It is not an elliptical. It has a ring, and rings are disk phenomena, requiring angular momentum and ordered rotation. But it is not a spiral either. It has no arms, no bar, no continuous stellar disk. It is something else, something that the hierarchical assembly model does not obviously produce. Where did the angular momentum come from that shapes the ring? Presumably from the same source that provides angular momentum to all rotating systems, from the tidal torques of neighbouring structures during the early stages of collapse. But those tidal torques produce spirals, not rings. They produce disks that extend all the way from the centre to the edge, not disks with enormous holes in the middle. Where did the gap come from? The hierarchical model has no clear answer. Gas falls inward under gravity. It does not spontaneously clear out of a region and stay cleared. Something must have removed the gas from the gap and prevented new gas from filling it. But what? Where did the star formation in the ring come from? Stars form from gas, and the ring is full of young blue stars, so there must be gas in the ring, gas that is actively forming stars right now. But the core is gas poor, dominated by old yellow stars. The gas was somehow confined to the ring and excluded from the core. By what mechanism? The questions multiply. Each answer required to explain Hoag's object requires its own explanation. The chain of causation stretches backward, and at its end we find nothing but initial conditions that seem improbably precise. This is not a failure of the hierarchical model exactly. The model does not say that Hoag's object cannot exist. It says only that Hoag's object should be very rare, the product of very specific circumstances, and that we should not expect to understand it without detailed knowledge of its particular history. But we do not have detailed knowledge of its history. We have only the end state, the geometry we observe, the ring and the core and the gap. We are trying to run the movie backward, to infer the cause from the effect, and the movie will not run. Too many possible paths lead to where we are. Too few of them can be distinguished with the data we have. The galaxy keeps its secrets, keeps them in plain sight, visible to any telescope powerful enough to resolve its structure, but invisible to the simulations that try to reproduce it. A geometric cipher, perfectly circular to within 1%, perfectly centred, perfectly empty where it should not be, perfect in ways that nothing should be perfect. And through the centre of that perfection, like an eye staring back at us from the abyss, another ring galaxy waits, smaller, fainter, impossibly aligned. A coincidence that compounds the mystery, a doubling of strangeness that makes the already strange even stranger. We will come back to that second ring. We will ask what it means that we can see through the centre of Hoag's object as if through a window, and find on the other side another structure that echoes the first. We will ask about the probability of such an alignment, about the composition of that distant ring, about what it tells us regarding the nature of the gap that permits us to see it at all. But first, let us pause here. With the simulations that fail, and the physics that does not predict, and the galaxy that should not exist but does. Let us sit with the silence of 75 years of unanswered questions. Let us feel the weight of a 1% deviation from perfect circularity, a precision that no model demanded and no process explains. The ring turns in the dark, 500 million light-years from the nearest major neighbour, isolated beyond any reasonable expectation, shaped by forces we cannot name into a form we cannot replicate. And somewhere in that turning, in that silence, in that impossible geometry, there is a truth about the universe that we have not yet learned. We are not finished failing to understand it. Now let us turn to the gap itself, the absence at the heart of Hoag's object, the darkness between the yellow core and the blue ring that should not be empty but is. In most galaxies, stars fill the space between the centre and the edge in a continuous gradient. The density falls off as you move outward, following mathematical curves that physicists have studied for more than a century, but it never simply stops. Even in spiral galaxies with their dramatic arms and their lanes of dust, the arms sit on top of a continuous disk. Between the arms, between the spirals, there are still stars, fewer perhaps, dimmer, but present. The disk is not perforated, the disk does not have a hole. Hoag's object has a hole, a vast circular annulus of emptiness, tens of thousands of light years across, separating the core from the ring as cleanly as if someone had erased the middle of the galaxy with a cosmic pencil. The surface brightness in the gap is so low that it falls below the detection threshold of many imaging surveys. Deep exposures reveal only the faintest hints of scattered light, and even those hints may be artifacts of the observation process itself, the glow of the atmosphere, the scattered light within the telescope, the noise inherent in any measurement of darkness. What remains when you subtract those artifacts is, for all practical purposes, nothing. Not the absence of dense star formation, not a region of slightly older, dimmer population, nothing. The gap is empty in a way that demands explanation. Consider what this means dynamically. Stars in a galaxy are not stationary. They orbit the centre, their paths determined by the total gravitational pull of all the mass interior to their position. The yellow stars in the core of Hoag's object are orbiting something. The blue stars in the ring are orbiting something. The gravity that holds them on their paths comes from the mass distribution of the entire system, including any mass in the gap, including the dark matter halo that presumably surrounds the galaxy like an invisible shell. If there is mass in the gap, it affects the orbits. Stars near the inner edge of the ring feel a gravitational pull from whatever lies between them and the core. Stars in the outer part of the core feel a pull from whatever lies between them and the ring. The motions of the visible stars encode information about the invisible mass distribution. This is how we detect dark matter in the first place. We watch how fast stars orbit, we calculate how much gravity is needed to keep them on those orbits, and we find that there must be more mass than we can see. The invisible mass reveals itself through its gravitational effect on the visible. In Hoag's object, the gap presents a puzzle. If the gap is truly empty of both visible matter and dark matter, then the gravitational profile should show a discontinuity. The stars at the inner edge of the ring should feel less pull than if the gap were filled. Their orbital speeds should reflect this. But if the dark matter halo extends smoothly through the gap, as it does in most galaxies, then why does the visible matter not follow? Why is there dark matter in the gap but no baryonic matter, no gas, no stars? The observations are difficult. Measuring the rotation curve of a ring galaxy requires spectroscopy precise enough to detect the Doppler shifts of stars and gas at different distances from the centre. For a galaxy 600 million light-years away, this is challenging work. The angular size of Hoag's object on the sky is small, about 16 arcseconds across, roughly the apparent size of a grain of sand held at arm's length. Resolving the velocity structure within that tiny patch of sky requires either extremely large telescopes or extremely long observation times, often both. The data we have suggests that the rotation curve is relatively flat, consistent with the dark matter halo that extends through the gap. But the precision is limited. The error bars are wide. We cannot definitively rule out more exotic mass distributions. We cannot say with certainty what lies in the darkness between the core and the ring. What we can say is that whatever process created Hoag's object somehow cleared the baryonic matter from the gap while leaving the dark matter in place. Or perhaps more accurately, whatever process created the core and the ring somehow deposited material in two discrete locations with nothing between. The gap is not erased. The gap is unfilled. The distinction matters. Imagine building a sandcastle on a beach. You scoop up sand and pack it into a mound in the centre. You scoop up more sand and build a wall around the mound, leaving an empty moat between. The moat is not empty because you removed sand from it. The moat is empty because you never put sand there in the first place. You deposited sand only where you wanted it, in the mound and in the wall, and left the moat untouched. Now imagine that instead of your hands, The only tools available were gravity and angular momentum and gas dynamics. Imagine that the sand was not sand, but hydrogen atoms falling together under their own weight over billions of years. Imagine that the moat had to stay empty not for an afternoon, but for the entire lifetime of the galaxy, 8 billion years or more, while the mound and the wall evolved independently. Imagine that any perturbation, any stray cloud of gas, any interaction with another galaxy, any internal instability, could fill in the moat and ruin the pattern. The moat stayed empty. The pattern survived. For 8 billion years. Stop and feel the weight of that. 8 billion years is not a human timescale. It is not even a civilizational timescale. It is a geological era repeated 1,000 times over. Mountains rise and fall, continents drift, species appear and vanish, entire branches of the evolutionary tree bud and wither. And through all of that time, measured not on Earth, but in the isolated darkness between galactic superclusters, the gap in Hoag's object has remained empty, the ring has remained circular, the geometry has remained perfect. Stability on this timescale is not automatic. It must be maintained. Something must prevent the perturbations that would destroy the pattern from accumulating. Something must keep the system in its improbable configuration, despite the entropy that works constantly to erode any structure into randomness. In most physical systems, stability comes from feedback mechanisms. A thermostat keeps a room at constant temperature by turning the heater on when the room cools and off when the room warms. An ecosystem maintains its balance through predator-prey dynamics, resource competition, the 1,000 interlocking checks and balances that prevent any single species from growing without limit. These feedback loops are not designed. They emerge from the physics and biology of the system, but they are there, invisible hands holding the system near its equilibrium. What feedback loop holds Hoag's object in its equilibrium? What mechanism prevents gas from falling into the gap, forming stars and gradually filling the emptiness? What process keeps the ring circular instead of letting it warp and twist into a spiral? We do not know. The observations tell us that the stability exists. The theory does not tell us how. One possibility is resonance. In orbital mechanics, resonance occurs when two bodies have orbital periods that form a simple ratio. The outer planets of the solar system are locked in resonances with each other. Moons around Jupiter and Saturn trace out patterns determined by the ratios of their orbital periods. These resonances can be stable configurations, valleys in the energy landscape, where small perturbations are corrected rather than amplified. Perhaps something similar happens in Hoag's object. Perhaps the stars in the ring and the stars in the core are locked in a configuration where their combined gravitational influence creates a resonant barrier, a kind of invisible wall that prevents material from crossing the gap. Perhaps the dark matter halo is structured in just the right way to create these resonances naturally. Perhaps the initial conditions of the galaxy's formation placed the material in positions that happen to fall into resonant configurations, and those configurations have persisted ever since. This is speculation. The detailed calculations required to test this hypothesis have not been done, in part because they would require knowledge of the mass distribution that we do not have, and in part because the problem is computationally expensive. Running a simulation of a ring galaxy for 8 billion years of dynamical time requires enormous computational resources. The number of particles needed to resolve the gap, the ring, the core, and the dark matter halo simultaneously pushes against the limits of what modern computers can handle. So the hypothesis remains untested, the gap remains unexplained, the stability remains mysterious. Let me try once more to give you a feel for the strangeness of this stability. Consider the Great Red Spot on Jupiter, a storm larger than the Earth, spinning in the atmosphere of the gas giant, observed continuously since at least 1830, and possibly as early as 1665. The longevity of this storm amazed scientists for centuries. How could a weather pattern persist for hundreds of years when storms on Earth dissipate in days or weeks? The answer, discovered through careful study and computer modelling, involves the detailed physics of Jupiter's atmosphere, the way energy is pumped into the storm from below, the way the planet's rotation creates stable bands of alternating wind direction. The Great Red Spot is a dynamical equilibrium, maintained by processes we now understand reasonably well. But the Great Red Spot is 400 years old at most. Hoag's object is 20 million times older. The gap in Hoag's object has been empty for 8 billion years. not 400. Whatever process maintains this stability operates on timescales that make the Great Red Spot look like a momentary fluctuation, and Jupiter is close. We have sent spacecraft to photograph the Great Red Spot from a few thousand kilometers away. We have measured its temperature, its composition, its wind speeds, its depth. We can study it with the luxury of proximity. Hoag's object is 600 million light-years away. We cannot send a probe. We cannot measure its internal dynamics directly. We can only watch the light that left the galaxy hundreds of millions of years ago and try to infer the physics from the photons. The isolation of the observer compounds the mystery. We are too far away to see clearly, too limited in our tools to probe deeply, too bound by the speed of light to gather more information. The galaxy exists in a kind of epistemic darkness, revealing just enough of itself to pose questions but not enough to answer them. This is a recurring theme in the study of Hoag's object. The questions are precise. The data are limited. The gap between what we want to know and what we can measure stretches across the same 600 million light-years that separate us from the galaxy itself. Now let us consider the mass, not just the distribution, but the total quantity. How much does Hoag's object weigh? This question turns out to be surprisingly difficult to answer. The standard technique for measuring galactic mass is the rotation curve method. Measure the velocity of stars or gas at different distances from the centre. Apply Newton's laws or their relativistic generalizations. Calculate the mass required to produce the observed velocities. The method works well for spiral galaxies with continuous disks of gas, where the velocity can be measured at every point along the radius. Hoag's object does not have a continuous disk. The gap disrupts the measurement. We can measure velocities in the core and velocities in the ring, but the gap is empty, devoid of the traces we need to probe the gravitational field in that region. The mass in the gap, whether dark matter alone or some combination of dark and invisible baryonic matter, must be inferred indirectly. Estimates vary. The total mass of Hoag's object has been calculated at somewhere between 100 billion and 1 trillion solar masses, depending on the assumptions used. The uncertainty spans an order of magnitude. For comparison, we know the mass of the Milky Way to within a factor of 2 or 3. We know the mass of the Andromeda Galaxy about as well. These are nearby galaxies, observed with every tool in our arsenal, measured by dozens of independent techniques. Hoag's object is measured by 1 or 2 techniques, applied at the edge of their precision, yielding estimates that cannot be reconciled without additional data. An order of magnitude uncertainty means we do not know whether Hoag's object is a relatively lightweight galaxy, comparable to the Large Magellanic Cloud, or a heavyweight, comparable to the Milky Way, or a true giant, among the most massive disk galaxies known. The core alone might contain as many stars as our entire galaxy, or it might contain a tenth as many. We cannot tell. This uncertainty propagates into every other calculation. The stability of the gap depends on the mass distribution. The formation history depends on the total mass. The age of the stellar populations depends on the star formation rate, which depends on the gas mass, which depends on the total mass. Everything is connected, and the uncertainty in one measurement infects all the others. The astronomers who study Hoag's object know this. Their papers are careful to hedge, to acknowledge the limitations, to note that their conclusions are provisional. The science is honest about its ignorance, but the ignorance is frustrating nonetheless. 75 years after Arthur Hoag first noticed this strange nebular object, we still cannot say with confidence how heavy it is. Let that sit for a moment. Think about what it means to study something for 3/4 of a century and still not know its basic properties. The mass of a galaxy is not some obscure technical detail. It is the most fundamental parameter, the quantity that determines almost everything else about the system. To not know the mass is to not know the galaxy, and yet we observe it. We photograph it. We publish papers about it. We give it a name and a catalogue number and a place in our databases. We speak of it as if we understood it, when in truth we understand almost nothing. This is not a failure of effort. The astronomers who study ring galaxies have worked hard, applied clever techniques, pushed their instruments to the limits. The failure is inherent in the problem. Hoag's object is too far, too faint, too strange to yield its secrets to our current tools. We are trying to read a book from across a chasm, squinting at letters we can barely make out, guessing at words that might be misprints or might be revelations. The gap in our knowledge mirrors the gap in the galaxy. Both are dark, both are persistent, both resist our attempts to fill them. Now consider the stars themselves, the blue stars in the ring and the yellow stars in the core. These two populations tell different stories, stories written in the physics of stellar evolution. Blue stars are hot and luminous. They burn their nuclear fuel rapidly, converting hydrogen to helium and helium to carbon in reactions that pour energy into space at prodigious rates. A blue giant might be 10,000 times more luminous than the Sun, outshining entire galaxies of smaller stars. But this brilliance comes at a cost. Blue giants consume their fuel quickly and die young, exploding as supernovae or collapsing into neutron stars and black holes after only a few million years. If you see a blue star, that star must be young. Not young in human terms, perhaps, but young in astronomical terms. A few million years old, maybe 10 million, maybe 50 million, not a billion, not 2 billion. Blue stars do not live that long. The ring of Hoag's object is full of blue stars. This means the ring is forming stars right now. Not 8 billion years ago, when the galaxy first took shape, but now, in the present moment. Or at least the present moment as we observe it 600 million years after the light left the galaxy. The ring is a site of active star formation, a nursery where new stars are being born from clouds of gas and dust. Yellow stars are cooler and dimmer. They burn their fuel slowly, stretching out their lifetimes across billions of years. The Sun is a yellow star, and it has been shining steadily for 4.5 billion years, with another 5 billion or so left before it exhausts its hydrogen and swells into a red giant. Yellow dwarfs and yellow giants can persist for 10 billion years or more, glowing with the patience of deep geological time. If you see a yellow star, that star might be old or young. Yellow stars can form in active star-forming regions, just as blue stars do. But a population dominated by yellow stars, with few or no blue stars mixed in, is almost certainly old. The blue stars that once existed have died. The yellow stars remain, the survivors of an ancient generation, glowing with the light of the distant past. The core of Hoag's object is dominated by yellow stars. The deep red tint visible in the best images comes from the light of millions of ancient suns, stars that formed billions of years ago and have been burning steadily ever since. The core is not forming new stars. It has not formed new stars for a long time. The gas that would fuel star formation is gone, exhausted or expelled, leaving only the stellar remnant of an earlier epoch. Two populations, two stories. The ring is young and active. The core is old and quiescent. They coexist in the same galaxy, separated by the gap, turning around the same centre, bound by the same gravity, but fundamentally different in character. This difference raises questions. How did the gas end up in the ring but not in the core? If the galaxy formed through hierarchical merging, where gas falls inward and forms stars from the centre outward, then the core should have formed first. But if the core formed first and consumed all the gas, where did the gas in the ring come from? Did it fall in later, from outside? Did it originate in the core and get pushed outward? Did it form separately, never passing through the inner regions at all? Each possibility has problems. Gas falling in from outside would need to settle into a remarkably circular orbit without disrupting the existing structure. Gas pushed outward from the core would need some mechanism to drive it outward against the pull of gravity. Gas forming separately would require initial conditions that place material precisely in a ring-shaped distribution, a geometry that no known process produces naturally. The stellar populations are clues, but clues to a puzzle we cannot solve. They tell us that the ring and the core have different histories, different ages, different trajectories through time. They do not tell us how those different histories came to coexist in the same structure. They pose questions without offering answers. We are not finished with the questions. We have not yet reached the deepest one, the one that sits at the centre of the gap like the second ring galaxy visible through the hole. But let me pause here and ask you to feel something. Feel the difference between looking at an object and understanding it. Feel the gap between observation and explanation. We have been looking at Hoag's object for 75 years. We have measured its size, catalogued its colours, estimated its distance, named its parts. We have all the appearances of knowledge. But the gap remains. The emptiness between observation and understanding stretches across the same impossible distance as the emptiness between the core and the ring. We are astronomers standing at the edge of a chasm looking across at a structure we can describe but cannot explain. The galaxy does not care about our confusion. It turns in the dark, 500 million light-years from anything, shaped by forces we cannot name into a form we cannot replicate. Its stability mocks our uncertainty. Its perfection defies our physics. Its very existence reminds us that the universe is not required to make sense. And through the centre of this inexplicable object, visible because the gap is empty, waiting to compound the mystery, another ring galaxy stares back. Let that settle for a moment. Through the centre of one impossible object, we see a second impossible object. The probability of this alignment, a ring galaxy positioned precisely behind another ring galaxy, visible through the empty space that should not exist, is so small that calculating it feels almost absurd. And yet there it is, in every deep image, an orange smear of ancient light framed by the gap that physics cannot explain. The second galaxy has a name, though it is not a famous one. Astronomers call it SDSS J546 713. 93.1351 6.8, a string of coordinates that tells you where to point your telescope and nothing else. It sits approximately 600 million light-years beyond Hoag's object, placing it at roughly 1.2 billion light-years from Earth. At that distance, the second ring galaxy is barely more than a smudge, a few pixels of colour in even the deepest exposures. But those pixels tell a story. The galaxy is yellow-orange, the colour of old stars, the colour of a structure that has not formed new suns in billions of years, and it is shaped, as far as we can tell from its faint image, like a ring. Two ring galaxies, one behind the other, both rare, both unexplained, both visible in the same frame only because the nearer one has a hole in its centre, large enough to see through. The odds against this alignment are staggering. Ring galaxies themselves are rare. Perhaps 1 in 1,000 galaxies shows the distinctive ring morphology, and most of those are collisional rings that look nothing like Hoag's object. Perfect ring galaxies, with clean circular symmetry and empty centres, are rarer still. The best estimates suggest that Hoag-type rings might constitute one galaxy in 10,000, perhaps one in 50,000. Nobody knows the true fraction because the sample size is so small. We have found perhaps a dozen galaxies that resemble Hoag's object closely, out of the millions of galaxies catalogued in modern surveys. Now consider the geometry. For the second ring galaxy to be visible through the centre of the first, it must fall within a very narrow cone of sky, the angular size of Hoag's gap as seen from Earth. That gap subtends roughly 17 arc-seconds, a tiny fraction of the full sky. The probability that any particular distant galaxy falls within that cone is about 1 in several hundred million. Multiply the rarity of ring galaxies by the narrowness of the alignment, and you get a number so small it approaches the absurd. And yet, the universe is vast. There are hundreds of billions of galaxies in the observable universe, and we have looked at millions of them in detail. Improbable things happen. The lottery has winners. But this particular improbability carries a different weight, because it compounds the mystery rather than resolving it. If Hoag's object were well understood, if we knew exactly how it formed and why it looks the way it does, then the background galaxy would be a charming coincidence, nothing more, a pretty picture, a cosmic photobomb. But Hoag's object is not well understood. Its formation remains a puzzle, and the presence of a second ring galaxy in the background raises an uncomfortable question. Is the alignment truly random, or does it hint at something we are missing? Let me be clear about what this question means and what it does not mean. There is no known physical mechanism that could connect two galaxies separated by 600 million light-years. They do not interact gravitationally in any meaningful sense. They do not share gas or stars. Their light reaches us from different epochs. The light from the background galaxy is 600 million years older than the light from Hoag's object by the time both reach our telescopes. In every physical sense that matters, the two galaxies are unrelated. The alignment is almost certainly a coincidence, but coincidences can be informative. If ring galaxies are more common than we think, then alignments like this become less improbable. If the formation mechanism for Hoag-type rings operates more frequently than our models suggest, then finding two in the same line of sight tells us something about the population statistics. The background galaxy, in this reading, is not a clue to the physics of ring formation. It is a clue to the demographics. It suggests that we may be underestimating how often these structures form, or the alignment is simply luck. The universe has dealt us an unlikely hand, and we are pattern-seeking creatures reading meaning into randomness. Both interpretations are possible. Neither can be confirmed. The background galaxy sits in the frame, beautiful and silent, offering no testimony. There is another way to think about this alignment, one that touches on something deeper. When you look at Hoag's object in a good image, your eye is drawn to the gap. The emptiness commands attention precisely because it is unexpected. Galaxies are not supposed to have holes. The gap violates our intuition about what a gravitationally bound structure should look like, and violation draws the gaze. We stare at the gap because we cannot understand it. And when we stare at the gap, we see through it. The gap becomes a window. The absence of nearby stars reveals distant stars. The local mystery frames a cosmic mystery. The geometry of Hoag's object, by being wrong, by being empty where it should be full, allows us to see farther than we otherwise could. Think about what that means. The structure that we cannot explain becomes the lens through which we observe other structures we cannot explain. The puzzle opens a view onto further puzzles. The emptiness is not just a feature to be explained, it is an opportunity for observation. If the gap were filled with stars, the background galaxy would be invisible, lost in the glare. The gap's existence is what makes the deeper universe accessible. This is not mysticism, it is geometry. But the geometry carries poetic weight whether we intend it to or not. The thing we do not understand is also the thing that lets us see farther. The absence in our knowledge corresponds to an absence in the sky, and through that absence more questions become visible. The universe is structured in layers, each one revealing the next, each mystery framing another mystery beyond it. Stop and feel the weight of that. We have been looking at Hoag's object for 75 years, and through its centre we can see 600 million light-years deeper into space. The gap is not just a problem to be solved, it is a portal. And through the portal, another ring galaxy waits, as if the universe is rhyming with itself, repeating a shape across unimaginable distances for reasons we cannot name. Now let us turn to the question that has haunted this investigation from the beginning. How did Hoag's object form? What sequence of events, what combination of forces, what initial conditions could produce a structure this symmetrical, this stable, this geometrically precise? The honest answer is that we do not know. But the honest answer is not the complete answer. Over the decades, astronomers have proposed several formation scenarios, each with strengths and weaknesses, each explaining some features of the galaxy while failing to explain others. Let me walk you through the main candidates, not because any of them is correct, but because their failures illuminate the depth of the problem. The first hypothesis, proposed shortly after Hoag's discovery, suggested that the ring is a gravitational lens, not a physical structure at all, but an optical illusion created by the bending of light around a massive core. In this picture, the yellow sphere at the centre would be an ordinary elliptical galaxy, and the blue ring would be the distorted image of a background galaxy whose light has been curved into a circle by the foreground's gravity. This hypothesis has a certain elegance. Gravitational lensing is real and well understood. It produces rings and arcs and multiple images all the time. Einstein rings, as they are called, can look remarkably circular when the alignment is perfect. If Hoag's object were a gravitational lens, then the mystery would dissolve. There would be no strange formation scenario to explain, no impossible dynamics, no gap that should not exist. Just two ordinary galaxies, one in front of the other, with gravity doing what gravity does. But the lensing hypothesis fails almost immediately when confronted with the data. For gravitational lensing to work, the background source must be at a very different distance from the foreground lens. The geometry requires it. And the blue ring in Hoag's object is not at a different distance from the yellow core. Both have the same redshift. Both are receding from us at the same velocity, which means both are at the same cosmological distance. They are part of the same structure, not an optical illusion created by foreground and background. Moreover, the blue ring shows resolved structure. Individual knots and clumps that are consistent with regions of star formation, not the smooth arcs that gravitational lensing produces. The ring has internal texture. It is a real population of stars bound together by real gravity, not a smeared image of something behind it. The lensing hypothesis is dead. It was tested and rejected. But its rejection clarifies something important. The ring is physically present. It is not an illusion. Whatever process created Hoag's object created a real structure, a genuine collection of stars and gas orbiting a common centre in a shape that should not exist. The mystery is not in our observation. The mystery is in the sky. The second hypothesis, and the one that remains most popular in the literature, involves a galactic collision. In this picture, a small disk galaxy passes through the centre of a larger disk galaxy, creating a density wave that propagates outward like a ripple in a pond. The wave compresses gas as it moves, triggering star formation in a ring that expands over time. This process is well documented. We see collisional ring galaxies throughout the universe. The Cartwheel Galaxy is the most famous example, a spectacular ring of star formation surrounding a disturbed core, clearly the product of a recent collision. Could Hoag's object be an ancient collisional ring, one that formed long ago and has since settled into its current configuration? The idea is attractive because it invokes known physics. Collisions happen, density waves form, rings expand. We do not need to invent new mechanisms to explain ring galaxies in general. But when we apply the collisional model to Hoag's object specifically, problems emerge. The first problem is the symmetry. Collisional rings are not perfect circles. They are typically elongated, distorted by the off-centre passage of the intruder galaxy. The collision imparts momentum that breaks the circular symmetry, producing rings that are oval or irregular. Hoag's object is not oval. It is not irregular. It is, to within the limits of measurement, a perfect circle. Whatever process formed the ring either involved a perfectly centred collision, the intruder passing directly through the rotational axis of the target, or something else entirely. Perfectly centred collisions are not impossible, but they are improbable. The targeting required is exquisite. The intruder must hit the bullseye, and it must do so with very little tangential velocity relative to the target. Miss by a small amount, and the ring becomes elliptical. Miss by a larger amount, and the structure disrupts entirely. The probability of a collision this perfect is low enough that we should not expect to see many examples, and yet Hoag's object is not unique. We have found other Hoag-type rings, other galaxies with the same geometry, the same impossible perfection. If collisional formation requires a 1 in a million shot, why are there multiple examples? The second problem is the gap. Collisional rings do not typically produce empty gaps. The density wave compresses gas into the ring, but it does not evacuate the space between the ring and the core. Collisional rings usually have diffuse stellar material throughout their interiors, a fading glow of stars that formed before the collision or in the immediate aftermath. Hoag's object has almost nothing in the gap. The emptiness is deeper than collisional models predict. The hole is too clean. The third problem is the core. Collisional rings form from disk galaxies, spirals with rotating disks of gas and stars. When the collision occurs, the disk is disrupted but not destroyed. The remnant should still show traces of its disk origin, rotation signatures, residual spiral structure, asymmetries from the collision itself. The core of Hoag's object shows none of these. It looks like a classical elliptical galaxy, spheroidal, smooth, slowly rotating or not rotating at all. If the core was once a disk, something has erased all evidence of that disk. The transformation would require additional processes beyond the collision itself, processes that are not included in standard collisional models. The fourth problem is time. Collisional rings are transient. The density wave expands outward and eventually dissipates. The ring spreads, thins, and fades over hundreds of millions of years. The Cartwheel Galaxy is perhaps 100 million years old, and already its ring is beginning to show signs of dissolution. Hoag's object, with its much larger ring, would need to be stable over longer timescales, perhaps billions of years, given the age of the stellar populations in the core. But collisional rings do not last that long. The model predicts a structure that should have dispersed ages ago. Either Hoag's object is much younger than its core appears, or the ring is not a collisional remnant at all. Each of these problems is individually manageable. You can tweak the collision parameters to improve the symmetry. You can invoke additional processes to evacuate the gap. You can propose transformation mechanisms for the core. You can adjust timescales and initial conditions, but the tweaks accumulate. The model becomes increasingly contrived, requiring a series of special circumstances that strain credulity. At some point, the cure becomes worse than the disease. You're no longer explaining Hoag's object. You're constructing a Rube Goldberg machine to reproduce its appearance. This is the dirty secret of theoretical astrophysics, and it applies far beyond this single galaxy. When a model requires fine-tuning, when you must set initial conditions precisely to reproduce observed features, the model is probably missing something. The fine-tuning is a flag. It indicates that the underlying physics is incomplete, or that the formation scenario is wrong. A good model should produce the observed structure robustly, across a range of initial conditions, without requiring miraculous coincidences. Hoag's object defeats this test. No model produces it robustly. Every model requires special pleading. The third hypothesis takes a different approach entirely. Rather than invoking collisions, it proposes that Hoag's object formed through internal processes, that the galaxy created its own ring through secular evolution, without any external trigger. Here is the idea. Imagine a disk galaxy with a bar, an elongated structure of stars running through its centre, like a rod spinning at the galaxy's heart. Bars are common. About 2/3 of all spiral galaxies show bar structures. The bar rotates with the galaxy, and as it rotates, it exerts gravitational torques on the surrounding gas. These torques can redistribute material, pushing gas outward into rings at specific radii, where gravitational resonances trap it. Bar-driven ring formation is well established. We see inner rings and outer rings in barred galaxies throughout the universe. The process produces rings that are roughly circular, stable over long timescales, and dynamically decoupled from the inner structure. On paper, this sounds like a good match for Hoag's object, but there is a problem. Hoag's object has no bar. If a bar once existed, it has since dissolved. Bars can weaken and disappear over time, destroyed by central mass concentrations or consumed by the growth of a spheroidal bulge. Perhaps Hoag's object once had a bar that drove gas into the ring and then vanished, leaving only the ring behind. This sequence of events is possible but difficult to model. The timing must work out correctly. The bar must persist long enough to create the ring, then disappear without disrupting the ring it created. The bar dissolution must be gentle, gradual, complete, and the end result must be a perfect sphere surrounded by a perfect circle, with nothing in between. Once again, we are in the territory of fine-tuning. The model can produce Hoag-type structures, but only under specific conditions that seem improbable. The bar must form, evolve, and dissolve in precisely the right sequence. The initial disk must have precisely the right mass distribution. The gas must settle into precisely the right orbit. Each requirement narrows the window of possibility until we are left with a sliver of parameter space, a razor-thin path through configuration space that leads to the observed outcome. And there is a deeper problem. Bar-driven ring formation typically produces rings that are still associated with disk structures. The rings are usually embedded in faint outer disks, surrounded by diffuse stellar halos, connected to the inner galaxy by spiral arms or other features. Hoag's object shows none of this. The ring floats in isolation, disconnected from the core, separated by a gap that contains almost nothing. The bar-driven model explains how rings form, but it does not explain how the gap got so empty. It does not explain the surgery that separated the ring from everything else. Let me pause here and name what we are encountering. This is a case study in the limits of explanation. We have three major hypotheses: gravitational lensing, collisional formation, and bar-driven secular evolution, and all three fail to fully account for the observations. Lensing is ruled out by the data. Collision and secular evolution can produce ring-like structures, but neither produces structures that look quite like Hoag's object, without invoking special circumstances that make the model suspect. The failure is not a failure of effort. Astronomers have worked on this problem for decades. Simulations have been run, papers have been written, parameters have been varied, and still the galaxy sits there, unexplained, turning slowly in the dark 500 million light-years away, its geometry mocking our physics like a mathematical proof that we cannot complete. There is a phrase that appears sometimes in scientific literature, usually buried in the discussion sections of papers. Further investigation is needed. It is a polite way of saying, we don't know. It is a placeholder for future understanding, a promissory note that someone someday will solve this problem. When you see that phrase applied to the same object for 75 years, it begins to mean something different. It begins to mean that the problem may be harder than we thought. It may require new physics, new observations, new ways of thinking. It may remain unsolved for decades more. Hoag's object is further investigation needed, written in starlight across 600 million light-years of empty space. And we have not yet reached the deepest question. We have discussed what Hoag's object looks like, how old its stars are, what hypotheses have been proposed for its formation, and why those hypotheses fail. But we have not yet confronted the question that underlies all others, the question that makes this galaxy more than an astronomical curiosity. Why is it stable? The ring has been turning for billions of years. The core has been sitting at the centre, spherical and quiescent, for even longer. The gap between them has remained empty, uncolonised by the matter that should have fallen in or spread out. The system has persisted, maintained its shape, held its geometry across cosmic time, and this persistence is perhaps the strangest feature of all. Gravity is not a sculptor. It does not carve shapes and preserve them. It is a simplifier, a homogenizer, a force that pulls everything toward the centre, till the centre grows fat with accumulated matter. A ring of material orbiting a central mass should not stay a ring forever. Perturbations accumulate, orbits drift, small instabilities grow. The ring should spread, thicken, fall inward, lose its sharpness over time, and yet. The ring of Hoag's object is sharp. Its edges are defined. Its circularity is preserved. After billions of years of orbiting the central core, the ring has not dissolved into a diffuse halo, or fallen inward to join the core or spread outward into the intergalactic void. It has maintained its geometry with a fidelity that seems almost intentional, as if some invisible hand were holding the stars in place, preventing the natural processes of gravitational relaxation from doing their work. There is no invisible hand. There is only physics, only the laws that govern matter and energy throughout the universe, the same laws that apply here on Earth and in the most distant galaxies we can observe. But somehow, those laws have conspired to produce this structure, and to keep producing it, moment after moment, orbit after orbit, for longer than complex life has existed on our planet. How? The answer, if it is an answer at all, lies in the mathematics of resonance. When objects orbit a central mass, their orbital periods depend on their distance from that mass. Objects closer to the centre complete their orbits faster than objects farther out. This is Kepler's third law, one of the oldest and most reliable tools in the astronomer's kit. It applies to planets orbiting stars, moons orbiting planets, and stars orbiting the centres of galaxies. The relationship is precise, mathematical, inescapable. Move something farther from the centre, and its orbital period increases. Move it closer, and the period decreases. There is no negotiation with this law. It is built into the fabric of gravitational physics. But here is where things become interesting. When many objects orbit together, not one planet and one star, but millions or billions of stars all orbiting a common centre, their individual orbital periods interact. Some stars complete an orbit in 50 million years. Others take 100 million. Still others take 200 million. As they move, they pass each other, overtake each other, fall behind each other in an endless gravitational dance, and as they pass, they tug on each other. Each star feels not only the pull of the central mass, but also the smaller transient pulls of every star it passes near. These tugs are small, infinitesimally small compared to the central gravitational force, but they accumulate over time. A star might be nudged slightly inward by one passing encounter, then slightly outward by another, then inward again, then outward. Over millions of years, these random nudges add up. The star's orbit changes. It drifts. This drift is the enemy of rings. A ring is a collection of stars all orbiting at roughly the same distance from the centre, all moving at roughly the same speed, all maintaining roughly the same geometry. But if each star is being constantly nudged by its neighbours, constantly pushed and pulled in random directions, the ring should dissolve. The stars at the inner edge should drift inward. The stars at the outer edge should drift outward. The ring should spread like a drop of dye in water, until the sharp boundaries disappear and only a diffuse cloud remains, unless the nudges are not random. This is the key insight, the mathematical heart of ring stability. If the perturbations between stars can be made to cancel out, if the pushes and pulls can be arranged so that they work against each other rather than accumulating, then the drift can be prevented, the ring can persist, and the way to make this happen is through resonance. Resonance in its simplest form is what happens when two periodic phenomena share a simple numerical relationship. When you push a child on a swing, you time your pushes to match the swing's natural period. Push at the wrong time, and you fight against the swing's motion. Push at the right time, and your energy adds to the motion, amplifying it. This is resonance. It appears everywhere in physics, in tuning forks, in radio circuits, in the shattering of wine glasses by opera singers, in the orbits of moons and planets and asteroids. It is one of the universe's fundamental organizational principles, a way for systems to lock into stable configurations that persist over time. In the context of galactic rings, resonance works like this. Imagine a ring of stars orbiting a central core. Each star has its own orbital period, but these periods are not completely independent. They are determined by the star's distance from the centre and by the total mass enclosed within that distance. If the distribution of mass is arranged in a particular way, if the central core has a certain density profile and the ring has a certain width, and the gap between them is a certain size, then the orbital periods of stars in different parts of the ring can be made to have simple, numerical relationships to each other. One star might complete exactly 2 orbits for every 3 orbits completed by another star. One might complete exactly 3 orbits for every 4 of another. These simple ratios are resonances, and they have a remarkable property. When stars are locked in resonance, the gravitational perturbations between them do not accumulate randomly. Instead, they repeat in regular patterns, reinforcing some configurations and cancelling others. The result is that certain orbital arrangements become self-correcting. A star that drifts slightly out of the resonant pattern feels a net force that pushes it back toward resonance. A star that wanders too far inward or outward is nudged back into line by the collective gravitational field of its neighbours. This is the principle that keeps Saturn's rings sharp. Saturn's rings are not solid structures. They are collections of billions of ice particles, each one orbiting the planet independently. Yet the rings have sharp edges, clean gaps, bright bands and dark lanes that have persisted for millions of years. The secret is resonance. The moons of Saturn, particularly small inner moons like Prometheus and Pandora, orbit at distances that place them in resonance with particles in the rings. When a ring particle drifts toward a resonant gap, the periodic gravitational tugs from these moons push it back. The moons act like shepherds, maintaining the ring structure not through physical contact, but through the accumulated effect of countless tiny gravitational nudges delivered at just the right moments. Could something similar be happening in Hoag's object? Could the geometry of the system be held in place by resonances between the ring stars and the central core? The mathematics suggests that it is possible, in principle. If the mass distribution is arranged correctly, resonances can stabilize ring structures over long periods. But there is a problem, and it is a significant one. Saturn's rings are maintained by external shepherds, moons that orbit outside or inside the ring edges, providing the periodic gravitational kicks needed to maintain the structure. Hoag's object has no such shepherds. The gap between the core and the ring is empty. There are no massive objects orbiting in that gap, no gravitational enforcers maintaining the boundaries. Whatever is stabilizing the ring must be intrinsic to the ring itself, built into its own mass distribution and orbital dynamics. This is where the problem becomes genuinely difficult. Self-maintaining resonances in stellar systems are possible, but they require a very specific initial arrangement. The ring must have exactly the right mass. The core must have exactly the right density profile. The gap must be exactly the right width. Get any of these parameters wrong, and the resonances break down. The ring spreads. The structure dissolves. The fact that Hoag's object has maintained its geometry for billions of years suggests that the initial conditions were somehow exactly right. But this raises an obvious question. How did those initial conditions arise? What process could have assembled a ring galaxy with precisely the parameters needed for long-term resonance stability? We are back to the formation problem, but now we can see it from a different angle. It is not enough to explain how a ring might form around a core. We must explain how a ring with the correct mass, the correct width, and the correct relationship to the core's density profile might form and persist, undisturbed, for billions of years. The probability space shrinks dramatically. The formation mechanism, whatever it was, must have been not only unusual but precise, delivering a system that was dynamically special from the moment of its creation. Let me give you a feel for how narrow this window might be. Astronomers who model ring stability have found that small changes in initial conditions lead to dramatically different outcomes. Increase the mass of the ring by 10% and the resonances shift. The ring begins to spread. Decrease the mass by 10% and different instabilities emerge. Change the concentration of the central core and the orbital periods change, breaking the resonant relationships that held the structure together. The parameter space for long-lived ring galaxies is not a broad plateau. It is a narrow ridge, a knife edge of stability surrounded by regions where the structure cannot persist. Hoag's object is balanced on that ridge. It has been balanced there for more than half the age of the universe, and we do not know how it arrived at this balance or why it has stayed there, or whether it will remain balanced for another 4 billion years or collapse into something ordinary next Tuesday. Stop and feel the weight of that. We are not talking about a galaxy that is strange but explicable. We are talking about a galaxy that is strange in a way that seems to require explanation, yet no explanation we have devised can fully account for what we observe. The formation mechanisms are uncertain, the stability mechanisms are precarious, the initial conditions are improbable, and yet the galaxy exists, serenely indifferent to our confusion, a ring of blue fire circling a golden core in the depths of intergalactic space. There is a temptation, when confronting a problem like this, to reach for the exotic. Perhaps Hoag's object is evidence of new physics, forces or fields that we have not yet discovered operating at galactic scales. Perhaps the standard model of gravity is incomplete, and the galaxy's stability reflects dynamics that our current theories cannot capture. This temptation should be resisted, or at least approached with extreme caution. Exotic explanations are seductive precisely because they are unconstrained. When you invoke unknown physics, you can explain anything, which means you explain nothing. The discipline of science lies in exhausting ordinary explanations before reaching for extraordinary ones and checking every assumption, and testing every parameter before concluding that something truly new is required. Hoag's object has not yet exhausted ordinary explanations. The simulations are not complete. The observations are not finished. The parameter space has not been fully explored. There may yet be a formation mechanism within standard physics that produces this geometry and maintains this stability, a mechanism that we have simply not discovered yet because we have not looked hard enough or modelled carefully enough. But the years keep passing, 75 of them now since Arthur Hoag first noticed the peculiar smear on his photographic plate, and the ordinary explanations remain incomplete, their edges ragged, their predictions imperfect, their assumptions questionable. At some point, and reasonable people can disagree about when that point arrives, the persistence of the mystery becomes itself a piece of evidence. Evidence that the galaxy is genuinely unusual, that it occupies a corner of possibility space that we did not expect to be occupied, that its existence is telling us something about galactic physics that we have not yet understood. Now let me tell you about the other ring galaxy. I mentioned it earlier at the beginning of this journey, but we have not yet confronted it directly. It is time. Look back at that Hubble image, the one that made this galaxy famous. Focus on the gap, on the vast empty annulus between the golden core and the blue ring. It is not entirely empty. There, in the darkness, tiny and impossibly distant, is another galaxy. It is not a foreground object. It is not a nearby galaxy that happens to line up with Hoag's object from our perspective. It is genuinely far away, so far that its light has travelled across additional hundreds of millions of light years to reach us, and it is, this is the part that strains credulity, another ring galaxy, not just any galaxy, a ring galaxy, visible through the gap of Hoag's object. The probability of this alignment is so low that it borders on the absurd. Ring galaxies are rare. The chance of finding one perfectly framed in the gap of another, both aligned with our line of sight, is like winning a cosmic lottery that should not have been winnable. And yet there it is, a tiny smudge of light in the darkness, a ring within a ring, as if the universe were indulging in a joke about recursive geometry. What does this alignment mean? The honest answer is probably nothing. Coincidences happen. In a universe containing hundreds of billions of galaxies, some of them will align in improbable ways simply by chance. We notice the alignments because they are striking, but we do not notice the vast majority of sightlines that contain no remarkable alignments at all. This is a form of observational bias called the anthropic effect, or selection effect. The remarkable cases are remarkable precisely because they are rare, but their rarity does not prevent them from occasionally occurring. The background ring galaxy is almost certainly a coincidence, a cosmic accident with no deeper significance. And yet, the alignment does something to the viewer. It creates a visual effect, a framing, that amplifies the strangeness of Hoag's object. The second ring galaxy is like an echo, a repetition of the same impossible geometry at a greater distance. It makes the universe feel patterned, designed, as if some organizing principle were at work that we cannot see. This feeling is an illusion. We know it is an illusion, but the illusion is powerful nonetheless. Looking at that image, seeing the ring within the ring, it is difficult not to feel that something is being communicated, some message encoded in light that has travelled for billions of years to reach us. This is the aesthetic dimension of Hoag's object, the aspect of it that transcends astronomy and enters the realm of art or philosophy, or perhaps even religion. The galaxy is beautiful in a way that very few objects in the universe are beautiful. It has the beauty of pure mathematics, of a theorem made visible, of abstraction given physical form. The golden core and the blue ring, and the empty gap and the distant echo. Together they compose an image that speaks to something deep in the human mind, something that responds to symmetry and order and the unexpected perfection of form. Astronomers are not supposed to be moved by beauty. We are supposed to be moved by evidence, by data, by the slow accumulation of facts that build toward understanding. But scientists are also human beings, and human beings are affected by what they see. There is a reason that the Hubble image of Hoag's object has been viewed millions of times, shared across social media, printed in popular books, displayed in museum exhibitions. The galaxy draws the eye, it holds attention. It makes people stop and wonder, even people who know nothing about galactic dynamics or stellar populations or gravitational resonance. The beauty is the hook, the entry point, the reason anyone cares about this object at all. Without the beauty, Hoag's object would be just another entry in a catalogue, interesting to specialists but invisible to the world. With the beauty, it becomes something else entirely, a symbol, an icon, a reminder of how strange the universe truly is. And perhaps this is the deepest lesson of the galaxy. Not its physics, not its formation, not its stability, but its power to make us feel small and curious and alive. We are creatures who look up at the night sky and see patterns. We are creatures who ask questions about what we see. We are creatures who build telescopes and cameras and spectrographs to answer those questions, then spend lifetimes puzzling over the answers. This is what we do. This is who we are. And when we turn our instruments toward Hoag's object, when we collect its ancient light and spread it across our detectors, we are participating in something that connects us to every human being who has ever looked up at the stars and wondered. The galaxy does not know we are watching. The stars do not care about our questions. The universe is not obligated to be comprehensible, and it is certainly not obligated to be beautiful. That it is both, that it offers us mysteries wrapped in symmetry, questions framed by elegance, feels like a gift, unearned and undeserved, dropped into our laps by the blind processes of cosmic evolution. Now let me tell you about the dark matter. I have saved this for last because it is the most speculative, the most uncertain, the most likely to be revised or rejected as observations improve. But it is also potentially the most important piece of the puzzle, the hidden variable that might explain what ordinary physics cannot. Dark matter, as you may know, is the name astronomers give to the invisible mass that pervades the universe. We cannot see it, we cannot touch it, we cannot detect it directly with any instrument we have built, but we know it is there because of its gravitational effects. Galaxies rotate faster than they should based on their visible mass alone. Galaxy clusters bend light more strongly than their stars and gas can account for. The cosmic web of filaments and voids that structures the universe on the larger scales requires dark matter to form. Without it, the gravitational pull would be too weak to collapse matter into the structures we observe. Every galaxy, as far as we can tell, is embedded in a halo of dark matter. The halo extends far beyond the visible edge of the galaxy, forming an invisible cocoon that shapes the galaxy's dynamics and evolution. The visible galaxy, the stars, the gas, the dust, the black holes, is like the tip of an iceberg. The dark matter halo is the vast bulk beneath the surface, unseen but essential. The shape of a galaxy's dark matter halo affects everything about how the galaxy behaves. If the halo is spherical, the galaxy tends to be stable and round. If the halo is elongated or lumpy, the galaxy can develop bars, warps, asymmetries. The distribution of dark matter determines the orbital speeds of stars at different radii, the stability of spiral arms, the persistence of rings. In many ways, the dark matter halo is the skeleton of the galaxy, the invisible framework on which the visible structure is built. What shape is the dark matter halo of Hoag's object? We do not know. Direct measurement of dark matter distributions is extraordinarily difficult. The best we can do is infer the distribution from its gravitational effects on visible matter, and for Hoag's object, the visible matter is itself so unusual that the inferences are uncertain. But there are hints, clues in the data that suggest something interesting might be happening. The rotation curve of Hoag's object, the graph of how fast stars orbit at different distances from the centre, shows an unusual pattern. In most galaxies, the rotation curve rises near the centre as the orbital speed increases with enclosed mass, then flattens at large radii as dark matter begins to dominate. Hoag's object shows a different pattern. The rotation in the core is what you would expect from a compact massive stellar concentration. The rotation in the ring is what you would expect from stars orbiting in that ring's gravitational field. But the transition between them, in the empty gap, is peculiar. The curve suggests that something is structuring the dynamics in that gap, maintaining the separation between core and ring, preventing matter from falling inward or spreading outward. Could the dark matter halo of Hoag's object be shaped in an unusual way? Could it have a shell structure, a distribution that creates gravitational barriers between the core and the ring? Some theorists have suggested this possibility, pointing out that if the dark matter were concentrated in specific radial zones, rather than smoothly distributed, it could create the dynamical conditions needed for ring stability. The dark matter shell would act like an invisible wall, preventing the ring from collapsing and the core from expanding, maintaining the empty gap as a permanent feature of the galaxy's architecture. This hypothesis is speculative. There is no strong evidence for shell-structured dark matter halos in any galaxy, and the mechanism by which such a structure might form is unclear. But it cannot be ruled out, and it offers a potential explanation for the stability problem that has no other obvious solution. Perhaps the visible strangeness of Hoag's object is the symptom of an invisible strangeness, a dark matter distribution as unusual as the stellar distribution that sits within it. If this hypothesis is correct, then Hoag's object becomes even more valuable as a scientific target. It would be not just a curiosity but a laboratory, a place where we might learn something about dark matter that we cannot learn anywhere else. The visible ring would be a tracer of the invisible shell, a marker of structure that exists in the darkness, beyond the reach of our telescopes but not beyond the reach of our inference. This is how science often works. The visible anomaly points toward the invisible cause. The symptom leads to the diagnosis. The strange galaxy, sitting 500 million light-years away, refusing to fit our models, might be telling us something not just about itself, but about the universe as a whole. We do not know yet. The data are incomplete, the models are uncertain, the hypotheses are speculative. But the inquiry continues. Astronomers are still observing Hoag's object, still running simulations, still proposing formation mechanisms and stability mechanisms and dark matter distributions. The galaxy that Art Hoag discovered in 1950 is still generating scientific papers in 2024. 75 years of study, and we are not finished. Perhaps we will never be finished. Perhaps the mystery will outlast us all, passed down to future generations of astronomers who will turn their better instruments toward that distant ring and ask the same questions we are asking now. What made this galaxy? Why is it stable? How did it come to be? And the galaxy will sit there, silent, turning slowly in the dark, 600 million light-years away, holding its secrets in the geometry of ancient light. And so we arrive at the heart of the matter. Not the heart of Hoag's object, that yellow sphere of ancient stars turning slowly in its own gravity, but the heart of what it means that such a thing exists at all. We have travelled through 75 years of observation and hypothesis. We have watched formation mechanisms rise and fall, collision scenarios tested and found wanting, accretion models proposed and abandoned. We have seen the ghost galaxy hiding in the gap, the second ring galaxy floating impossibly in the centre, like a message written in the geometry of space itself. We have confronted the stability problem, the simulation problem, the dark matter shell hypothesis that might explain everything or might explain nothing at all, and now we must ask the question that has been hovering beneath all the other questions, the question that makes Hoag's object more than a scientific curiosity, more than a puzzle for professional astronomers to solve in their spare time between studying more tractable galaxies. What does it mean that we cannot make this? Let that question sit with you for a moment. We are a civilization that has decoded the cosmic microwave background radiation, mapped the distribution of dark matter in galaxy clusters, detected gravitational waves from colliding black holes 1 billion light-years away. We have built supercomputers that can simulate the formation of thousands of galaxies simultaneously, tracking the motion of billions of particles across billions of years of cosmic time. We have modelled the interiors of stars, the dynamics of planetary systems, the evolution of life, the folding of proteins. We have reached into the fabric of reality and pulled out equations that work, that predict, that explain. And we cannot reliably make a ring galaxy with a near-perfect circle surrounding a near-perfect sphere. Not by accident, not through any natural process our simulations can reproduce without intervention, not through any formation mechanism that arises from the physics we know, applied consistently across cosmic time. The ring galaxies our computers make are lopsided. They are asymmetric. They have the signs of their violent origins written in their structure. They look like what they are. The wreckage of collisions, the debris fields of cosmic accidents, the scars of gravitational trauma. Hoag's object does not look like a scar. It looks like something someone designed. Now let me be clear about what I am not saying. I am not suggesting that Hoag's object was designed. I am not proposing alien architects or cosmic engineers or supernatural intervention. The galaxy is almost certainly the product of natural processes, processes we do not yet fully understand, processes that may have required a precise and unlikely combination of initial conditions, but processes that operate through the same physics that governs everything else in the universe. The mystery is not whether Hoag's object is natural. The mystery is why nature would produce something that looks so deliberately artificial. This is a different kind of uncomfortable. The universe is not obligated to produce messy results. Nothing in the laws of physics says that all galaxies must be asymmetric, all structures must be irregular, all forms must bear the marks of their chaotic origins. Perfect spheres occur in nature. Perfect circles occur in nature. Soap bubbles are spheres. Planetary orbits are ellipses that can approach circles. Water droplets in microgravity form perfect spheres because surface tension minimizes their surface area. Nature knows how to make symmetric things when the physics demands it. But galaxies are not soap bubbles. They are not water droplets. They are systems of hundreds of billions of stars moving through complex gravitational fields, influenced by dark matter halos, disturbed by neighbours, evolving over billions of years through processes that accumulate small asymmetries into large ones. The default state of a galaxy, the state it would naturally evolve toward given any realistic initial conditions, is something lumpy and irregular and marked by its history. A galaxy should look like what it has been through. A galaxy should wear its past on its structure the way a face wears its age in its lines. Hoag's object does not wear its past. Hoag's object looks like it was manufactured yesterday. And this is the geometric horror I have been trying to lead you toward across these past hours. Not horror in the sense of fear or disgust. Horror in the sense of cognitive disruption, of category violation, of encountering something that your mind insists should not exist and yet demonstrably does. The horror of the uncanny valley, where something looks almost right but is wrong, in ways that your pattern-matching systems cannot quite articulate. The horror of finding a perfect clock in the ruins of an ancient city. Not horror that the clock is malevolent, but horror that the clock requires an explanation you cannot provide. Hoag's object requires an explanation we cannot provide. 75 years. 800 million stars in the core, 100 million stars in the ring, a gap so clean you could hide galaxies in it, and one galaxy does hide in it, another ring galaxy, as if the universe were winking at us through the cosmic microwave background. 320,000 light-years across. 8 billion years of stability. Every simulation that tries to reproduce it either fails outright, or requires such precise initial conditions that the probability of those conditions arising naturally becomes vanishingly small. Every formation mechanism that has been proposed either contradicts the observed properties or raises new questions as troubling as the ones it answers, stop and feel the weight of that. We are not talking about a mystery that will be solved next year when better telescopes come online. We are not talking about a gap in our knowledge that will be filled when the next generation of supercomputers runs the next generation of simulations. We are talking about a fundamental puzzle in our understanding of how galaxies form and evolve. A puzzle that sits 500 million light-years away, visible to amateur astronomers with modest equipment, and yet remains as opaque to professional astrophysicists as it was when Arthur Hoag first noticed it on a photographic plate in 1950. Some mysteries get harder with time. This is one of them. When Hoag discovered the object, astronomers did not yet know that dark matter existed. They did not have supercomputers to run n-body simulations. They did not have access to the deep surveys that would eventually reveal how rare ring galaxies are, how unstable they should be, how difficult they are to produce through any natural mechanism. In 1950, it was possible to look at Hoag's object and assume that we simply did not yet understand galaxy formation well enough, that the mystery would dissolve as our knowledge grew, that the strange ring was a temporary puzzle that would eventually become a textbook example of some well-understood process. That assumption was wrong. Our knowledge grew, our understanding deepened, our simulations became more sophisticated, our observations more precise, our theories more comprehensive, and the mystery did not dissolve. The mystery sharpened. Every advance in our understanding of galaxy formation made Hoag's object more anomalous, not less. Every improvement in our ability to simulate galactic dynamics made the ring's perfection more improbable, not more explicable. The more we learned, the stranger the galaxy became. This is not how scientific mysteries usually work. Usually increased knowledge reduces mystery. Usually better data constrains hypotheses. Usually improved simulations reveal the mechanisms behind observed phenomena. Hoag's object inverts this pattern. It is a mystery that grows with our understanding, an anomaly that becomes more anomalous as our baseline becomes more secure. And there is something almost existentially disturbing about that. We expect the universe to become more comprehensible as we study it. We expect our models to converge on reality, our simulations to match observations, our theories to explain what we see. Hoag's object refuses to cooperate. It sits there in the constellation Serpens 600 million light-years away, and it says, "No, your models are not complete. Your simulations are not sufficient. Your understanding is not deep enough. You have not yet grasped whatever principle made me." Perhaps we never will. Let me tell you what the optimists hope. They hope that the James Webb Space Telescope, with its infrared eyes that can peer through cosmic dust and see ancient light with unprecedented clarity, will reveal something new about Hoag's object. They hope that spectroscopic observations of the ring and the core will nail down the stellar populations, the ages, the metallicities, the formation histories, and that this data will constrain the formation mechanism to something we can reproduce in simulations. They hope that better rotation curve measurements will reveal the structure of the dark matter halo, confirming or ruling out the shell hypothesis, telling us whether the invisible matter is shaped as strangely as the visible matter. They hope that future surveys will find more ring galaxies like Hoag's object, not just ring galaxies in general, of which we know many, but ring galaxies with the same extreme symmetry and the same clean separation between core and ring. If we find more examples, we can study them statistically, look for common features, identify the conditions that produce this class of objects. These hopes are reasonable. Science has surprised us before. Mysteries that seemed permanent have dissolved in the light of new observations, new theories, new approaches. The history of astronomy is filled with objects that seemed inexplicable until suddenly they were explained. Puzzles that resisted solution for decades until a key insight made everything click into place. Perhaps Hoag's object is one of these mysteries, waiting for its key insight, waiting for the telescope or the theory or the simulation that will make its existence seem obvious in retrospect. But the pessimists have a different view. They point out that we have been studying ring galaxies for half a century, running ever more sophisticated simulations, and we have not gotten closer to reproducing Hoag's object. They point out that the object's perfection is so extreme that any formation mechanism capable of producing it would also predict other symmetry-perfect structures that we do not observe. They point out that the stability problem has no obvious solution, that the ghost galaxy in the gap remains unexplained, that every step forward in understanding generates 2 steps backward in explaining what we see. Perhaps Hoag's object is not waiting for a key insight. Perhaps Hoag's object is waiting for a revolution. In the history of physics, there have been moments when an apparently minor anomaly turned out to be the crack in the foundation of an entire theoretical framework. The orbit of Mercury, precessing just a little more than Newtonian mechanics predicted, turned out to require general relativity to explain. The blackbody radiation spectrum, deviating subtly from classical predictions, turned out to require quantum mechanics. The rotation curves of spiral galaxies staying flat where they should decline turned out to require dark matter, or perhaps a modification to our theory of gravity itself, a debate that continues to this day. Could Hoag's object be this kind of anomaly? Could its unexplained symmetry be pointing towards some gap in our understanding of galactic dynamics, some missing piece in our theory of gravity, some overlooked aspect of dark matter physics? Could the reason we cannot reproduce this galaxy in simulations be that our simulations are missing something fundamental, something that operates at galactic scales and reveals itself only in extreme cases like this? This is speculation. I want to be clear about that. There is no evidence that Hoag's object requires new physics. There is no consensus among astronomers that the ring galaxy's anomalous properties point toward any theoretical revolution. The object is strange, yes. The object is unexplained, yes. But many things in astronomy are strange and unexplained, and most of them turn out to have mundane explanations that simply take time to discover. And yet, the universe does not owe us comprehensibility. The universe does not guarantee that all its phenomena will fit neatly into our models. The universe is under no obligation to be explicable in terms of the physics we have already discovered. We have solved many puzzles, yes, but we have also encountered puzzles that remain unsolved, phenomena that resist our best theoretical efforts, objects that sit at the edge of our understanding and decline to be understood. Hoag's object may be such a phenomenon. It may be a messenger from the limits of our knowledge, an envoy from the territory we have not yet mapped, a reminder that the cosmos contains structures and processes and possibilities that exceed our current imagination. Think again about that second ring galaxy, the one floating in the centre of Hoag's object, visible through the gap like an eye through a keyhole. PGC 5 bottom 4 5 9 they call it, though that clinical designation hardly captures what the object represents. A ring galaxy inside a ring galaxy, a perfect circle seen through a perfect circle. The odds of this alignment occurring by chance are almost too small to compute. 1 in millions, perhaps 1 in billions, a cosmic coincidence that strains credulity. And yet, there it is. Some astronomers look at that alignment and see luck. The universe is vast. Improbable things happen. Somewhere in the observable universe, the improbable coincidence of a ring galaxy appearing inside another ring galaxy's gap was bound to occur, and we are simply fortunate that Hoag's object happens to be within range of our telescopes. Other astronomers look at that alignment and see a question. What if the alignment is not coincidental? What if there is something about the geometry of Hoag's object that makes it more likely to contain another ring galaxy in its line of sight? What if the same unusual conditions that produced Hoag's object also produced PGC 55459, and their apparent proximity is evidence of some shared origin, some common cause, some underlying structure in the universe that produces ring galaxies in clusters rather than at random? We do not know. The data do not tell us. The alignment sits there, unexplained, like everything else about this galaxy. And perhaps that is the final lesson of Hoag's object. Perhaps the ring galaxy in Serpens is not asking us to solve it. Perhaps it is asking us to sit with the unsolved, to accept the unexplained, to acknowledge that the universe contains phenomena that exceed our current understanding and may exceed any understanding we will ever achieve. This is hard for scientists. The scientific enterprise is built on the conviction that nature is comprehensible, that phenomena have explanations, that patient inquiry will eventually reveal the mechanisms behind observations. To suggest that some mysteries may be permanent, that some questions may have no answers accessible to human minds, feels like a betrayal of the scientific spirit. But humility is also part of science. The recognition that our models are approximations, that our theories are provisional, that our understanding is always incomplete. This recognition is not weakness, it is honesty. The scientist who admits the limits of current knowledge is not giving up on science. They are practicing it in its most authentic form. Hoag's object invites this kind of humility. It says, "Look at me. I am real. Your telescopes can see me. Your spectrographs can analyze me. Your computers can model me, and yet you do not understand me. After 75 years of study, you cannot explain how I formed, why I am stable, or why I look the way I do. I am a mystery in plain sight, an unsolved puzzle hanging in the darkness, and I will remain here long after you're gone. 600 million light years away. 8 billion years of existence. A ring so perfect it looks like a blueprint. A core so spherical it looks like a design. Art Hoag looked at a photographic plate in 1950 and noticed something strange. He wrote a paper about it, asked his colleagues for opinions, catalogued the object as unusual. He could not have known that he was launching a 75-year inquiry that would still be unresolved at the time of his death and beyond. He could not have known that the faint smudge on his photograph would become one of the most puzzling objects in extragalactic astronomy. He could not have known that generations of astronomers would turn their telescopes toward his discovery and come away more confused than when they started. And perhaps that is his real legacy. Not the discovery itself, but the question it opened. The question that remains open. The question that will remain open for as long as there are astronomers to ask it and telescopes to gather the ancient light. What made this galaxy? The universe answers with silence. The ring keeps turning. The core keeps glowing. The gap remains empty, clean, inexplicable. And somewhere in that gap, floating like a message in a bottle, another ring galaxy turns on its own axis, bearing its own stars, holding its own mysteries, as if the universe wanted to remind us that even our mysteries contain mysteries, that the unknown hides further unknowns, that the deeper we look, the more we find that we cannot explain. Let that settle over you as the night continues. 600 million light-years away, there is a galaxy that looks like nothing else we have ever seen. A yellow sphere of ancient stars surrounded by a blue ring of young stars, separated by a gap so clean it seems designed. A structure that no simulation can reliably produce. A stability that no model can fully explain. A symmetry that verges on the artificial, though we know it must be natural because what else could it be? And in the centre, through the gap, another ring galaxy floats, as if the universe were looking back at us through a window, asking us what we see, asking us what we understand, asking us to sit with the unsolvable and find peace in the presence of the unexplained. Perhaps we will solve it someday. Perhaps a future astronomer, with tools we cannot imagine, will look at Hoag's object and see what we have missed, will run a simulation that finally captures its geometry, will propose a formation mechanism that makes sense at last. Or perhaps not. Perhaps Hoag's object will outlast our theories, outlast our civilization, outlast the species that first noticed it and asked what it was. Perhaps the ring will keep turning for another 8 billion years, long after the last telescope has gone dark and the last question has faded into silence. The stars do not care about our confusion. The geometry does not require our approval. The universe is under no obligation to make itself comprehensible, and sometimes it produces objects that remind us of this in the most striking way possible. A perfect ring, a perfect sphere, a gap that defies explanation, a mystery that has no answer, or perhaps an answer we are not yet equipped to hear. And so we leave Hoag's object where we found it, turning slowly in the constellation Serpens, 600 million light-years from Earth, holding its secrets in the arrangement of ancient light. The ring is still there, bright with young blue stars. The core is still there, warm with old yellow stars. The gap is still there, empty and clean and impossible. And somewhere through the centre, another ring galaxy floats, like a question inside a question, like a mystery contained within a mystery, like the universe whispering to anyone patient enough to listen. You have not yet understood. Keep looking, keep asking, keep wondering. The darkness is full of things you have not yet seen, and some of them are shaped like nothing you have ever imagined, and they are real, and they are waiting, and they do not need you to explain them to exist. Hoag's object will be there tomorrow. It will be there next year. It will be there when you're gone, and when everyone you know is gone, and when the very concept of astronomy has changed beyond recognition. The ring will turn, the core will glow, the gap will remain, and the question will still be open, hanging in the dark, unanswered and perhaps unanswerable, as patient as the light that carries it across 600 million years of space to reach your eyes. Right now, In this moment, in this darkness, in this night that is shared across the universe, wherever anything looks up and wonders what the silence means.